alive after dinner of yesterday. So Adrian and myself will chair this session. The title of the session is Advances in the Use of EO for Land Surface and Hydrological Modeling. So we have 5 presentations. The first presentation is from Federico Di Paolo. So I think you will say your title, but it will be about snow monitoring. So you have 20 minutes, but including questions. So
Okay.
I don't know how much, if you are a good student or bad student, but if you
Oh,
want
we'll
questions
see.
on the...
Otherwise, the question will be kept for.
Yeah, okay. So if
No,
at
the final
18
discussion. Don't know.
18 minutes, if you don't have finished, we will make some noise.
Yes, of course. Great. Okay. Okay, this is also laser. But I think I need to.
Is it you, right? This one?
Ah, pensavo era già aperto.
Vabbè, faccio proprio. Vai?
Posto. Okay, so good morning. I'm Federico Di Paolo from the Mobi GIS company, and I will describe you some results coming from the integration of Earth observation data and a physical model for the monitoring of the evolution of snow. So we are a startup in Italy, in the north of Italy, located nearby the mountains. And we use our expertise concerning, of course, satellite data, physical modeling, machine learning for the study of the hydrological cycle. So from the precipitation through the melting down to water management for both extreme event prediction, or let's say mitigation, and other kind of water management related topics. So let's jump to the modeling of snow. Basically, the typical approaches are 3. The statistical one, dealing with in situ data. But of course, the limitation associated to this kind of method is the cost of installation and maintenance of the instrument, as well as the spatial coverage that is not wide nor continuous in space. Then there is the approach using physical models that, of course, can cover wide areas, but have some other kinds of limitations. For example, needs a ground truth. And then there is the so-called pure EO approach that is powerful, but of course have some other limitation. As an example, the effect of clouds on optical images, as well as the poor revisit time. So our idea is to mix the three models. So during the ESA-EO for Alps Snow project, we have developed an approach integrating a physical model with satellite and in situ data. So the idea is to use the pros of one of these kind of approaches. For example, the physical model embeds inside it all the constants and the parameters. And we also use the power of adding the satellite data as well as the snow gauges data, but without suffering the limitation on these ones. The physical model that we use is the geotop model. That is a distributed full energy balance model solving the equations for the snow evolution. So from the accumulation through the compaction to the melting. And of course, making some kinds of approximation. In particular, we do not consider the effect of wind and gravity. And for such a reason, we do not use a super high resolution. We use a 250-meter resolution that is pretty good. But for final resolution, the effect of such kind of quantities in the equation would be important at local scale. Imagine we are in a mountain, very narrow valleys, so the effect at local scale are very important. So basically, our physical model takes into as input the weather data that can be either reanalysis data or numerical weather prediction. And the output is the time series of snow depth, snow melt, and snow water equivalent. And of course, as said, this kind of model takes into account the full complexity of the morphology of the terrain as a function, of course, of elevation, aspect, and slope, and so on. Now, let's consider our approach consisting in different levels of simulation. Now, let's consider the first one, the simpler one, the so-called level 0, that uses as input just the ERA5 reanalysis. I will show you some results coming from the reanalysis, but you can think about it in a real-time way or in a forecast. It is pretty similar. So in this case, we have only this input to the physical model. Then we have the so-called level 1 simulation that integrates also the satellite data as input, and of course can be performed basically everywhere, because of course now we have wide coverage of satellite images over the world, and also a good historical data, at least 7 years of Sentinel-2, more or less. And then there is the level 2 that is integrating also the snow gauges data in the model. In particular, we assimilate the temperature, the precipitation mass, and the depth of the snow. So regarding the satellite data, we need to provide the physical model with maps like this. So basically binary snow cover area maps. So we need to have a pixel that is fully, completely snow covered, so over the ridges and at high elevation, and then a snow-free pixel at low elevation down to the valley. And because of course the images must be, let's say, consistent with the physics that is expected by the physical model. And this information can be translated in the snow line, as well as the snowfall line, and also the melting rate. In particular, we use this kind of information to retrieve the melting rate in this way. We compare the satellite image with the simulation, and we evaluate the bias between the two as a function of both the elevation. You can see here, as a function of the elevation, the snow cover area as a percentage for the two data set. And we do the same thing, but as a function of the main aspect. And then we correct the melting rate in the physical model from the result of this analysis through an iterative process. Let's take an example. We can see here, the red one is the satellite. So it's saying that over the 4 direction, the snow is present down to about 600 meters. But the simulation gives less snow. So we have to correct the melting rate. We do it, then we do the simulation again, and this is the result. Now we have more snow. The result of the simulation is moving toward what is observed by the satellite. So we do, if necessary, an iteration more in order to be as closer as we can to the Earth observation image. Now let's consider the effect of the assimilation of in situ data. In this case, this is a process that is made on a local scale, because it's a one-dimensional data. Then there will be converted in a two-dimensional data. Basically, we ingest to the model this kind of information, the time series of the snow depth, as well as the time series of the temperature and the precipitation mass that you can see here. And we use this kind of data to correct the mass of the snow. So again, we use an iterative process. We compare the result coming from the in situ gauge and the simulation. We check the phase first, because maybe we can have too much or too less snow because of the temperature. We correct the phase, and if needed, then we correct the mass. And this is an example. You can see here the lowest line in chain that is far away from the result, and then moving to the final iteration, the dark blue line, we are closer to the in situ data. Another example here, you can see the same thing. That, of course, is not always perfect. And this is another case, and you can see that the dark blue line is closer to the red one, to the snow gauge data. So as a quick recap, we use this kind of data to retrieve the mass, so to correct missing mass or too much mass using the in situ data, and we use the satellite data to correct the melting rate. You can see here the slope is different in the simulation and in the in situ data. Consider that the mass could be corrected also using the satellite data, but this is not implemented at present. So I will show you some results. We studied 2 square areas having located in the north of Italy. So this is basically the Lombardia region, and this is the Trentino Alto Adige. And we considered 2 winters. The 2013-14, that was a very snowy winter, and conversely, the 2016-17, that was poor in snow. Regarding the satellite maps, we used the snow cover area maps retrieved by the colleagues of EURAC Research coming from MODIS and having a resolution of 250 meters. So let's have a look at the results. You can see here the time, and in the upper plot, you can see the snow cover area as a percentage. And you can see in red the satellite, so our ground truth, and in magenta maybe the level 0. So and here you can see the bias between the two. And of course you can see that the bias is usually towards positive values. So basically we are overestimating the presence of snow, and this is probably due to the ERA5 input. So that's why it's important to assimilate some other kind of data, because if our input is biased, our result will be biased as well. So we assimilate the satellite data, and you can see that the bias is reducing. Not always, but usually is reducing. Then we assimilate also the in situ data, and you can see that the bias is reducing even more. Sometimes, in this case, is going toward negative biases, but basically the effect is pretty good. You can see the same thing on the second area during the same winter, where the level 1 simulation is better than the level 0, and the level 2 is better than the level 1. And similar results also for the other considered year, 2016-17. So, okay, we're pretty happy with these results. This was expected. And now let's have a look at another case, because I think that the information contained in the satellite data is even more important. You can see here, this is another simulation associated to the EO4Alps snow project. And you can see here that the reduction of the bias due to the assimilation of the satellite data is even higher. This is probably due to the fact that we used here Sentinel-2 images. So the resolution is higher than the one contained in MODIS. So local effects are approximated in a better way. And also the processing was different here because we used a dedicated process in order to reduce, to retrieve, let's say, optimized snow maps. So the result could be even better if we dig further in the satellite snow maps. So let's now have a look at the results in terms of local scale. So I will show you some metrics regarding the snow depth, comparing the levels of the simulation to the data measured by the snow gauges. So the metrics are the root mean square error and the mean absolute error. And if you think that these metrics are pretty poor, please consider that we didn't remove any problematic in situ data. You will see in the next slide what I'm talking about. So basically, these metrics must be better. But anyway, we had been very conservative here because we just want to see if the adding more data in the assimilation for the physical model is going to improve the results. And as expected, the level 1, so the assimilation of the satellite data, is not going to enhance the performance at very local scale. And this was, of course, expected because we are taking in consideration a very big area. So the effect of the satellite is globally okay, but locally can be not so good. Conversely, the assimilation of the in situ data at local scale is important and enhance highly the performance of our result. This is what I was talking about. We didn't remove snow gauges like this. So in this case, we do not have any data in the first months. So the bias between the simulation and in situ data must be huge, and also could prevent the correction of the data, because in this case, the sooner we start the assimilation and the correction, the better will be the final result, because of course the time series here is important. If we start correcting the data here, we are now too far to go towards the in situ data. That's why the metrics are so, let's say, so bad, or at least not optimal. But you can see here how, with respect to the level 0 and 1, when we add the in situ data to the assimilation, our final result, the green line, is closer to the snow gauge. Same results in to other sites, where you can see that the effect of adding the in situ data is very, very important. So concluding, we have developed this kind of methodology during the ESA-EO for Alps Snow project, and we also used the same methodology improved for the ESA DTA project. I think there will be a presentation regarding this project maybe in the afternoon. And also we use the same technology to develop our so-called JSnow platform that has been also awarded by my Hydrospace competition award last summer. So concluding, I think this approach is pretty good because it uses the integration of a physical model with different kind of data, so enabling a real-time monitoring of the snow evolution without suffering the limitation of each kind of approach. It can be used to follow the water cycle completely. So we retrieve finally the snow melt and the evaporation that can be further used as an input for another kind of digital twin, as we will see in the presentation of the DTA project. And of course, the accuracy is pretty high if we use a lot of data to drive the physical model. As a recommendation, I will suggest to use the Earth observation data also to retrieve the snowfall line. So in this case, it will be possible to correct the snow mass using only satellite data. Of course, if we add also the in situ data, we expect to have a higher accuracy. And other two important things, I think this kind of technology is scalable over the entire world because, of course, we have a lot of satellite also having high resolution, right? Sentinel-2 or also Landsat. So basically, there is no mountain range that cannot be studied through this approach. And of course, feeding the physical model with numerical weather prediction, we can go also in forecast. So that's all, and I hope you enjoyed the presentation.
Okay, thank you very much. It was exactly 20 minutes, so I will keep the question for the discussion for the seed question,
Okay.
and certainly there are some on the seed question we prepared with Adrien, some about a combination of data-driven models, and EO is one of them. So it will be interesting to have your feedback on this.
Okay, great.
Thank you. So our next speaker is Debbie Prasad, a postdoc researcher in ERP, CNR. And he will talk about assessing the utility of multi-mission satellite data into a hydrological model and for calibration purposes.
Good morning, everyone. I am Devi Prasad Sahu, currently working as a postdoctoral researcher in EPCNR. I'm acknowledging my co-authors. This is the work which is being carried out by me and Andrila under the supervision of Professor Sahu and Dr. Angelica. So, coming to a catchment scale analysis, for catchment scale water balance analysis, we need to identify the hydrological fluxes in that particular basin occurring at real time. So remote sensing gives us that opportunity to monitor that hydrological fluxes like precipitation, evapotranspiration, soil moisture, and those are really in previous presentations where remote sensing could good enough to capture all the dynamics along these variables. And we have also static variables that could be retrieved from the remote sensing, like the soil information and the land use cover information. So all these variables could be used for hydrological model setup. And for any hydrological model setup, we need to have the proper hydrological model calibration. And for this calibration or the parameterization of the hydrological model, we need to have the proper in situ discharge. But the problem is the in situ discharge. Like we have seen in several presentations, the gauging station information is steadily declining across the globe because of the maintenance of those gauging stations, at the same time, the remoteness of the gauging station, mishandling of the electronic sensors. So all these difficulties lead to declining in the gauging station across the globe. However, this river discharge could be monitored by remote sensing. So the question came, can we use this remote sensing based river discharge to calibrate the hydrological model? So we frame the research questions like this. Can we calibrate the remote sensing based river discharge? Can we calibrate the hydrological model using the remote sensing based river discharge? And at the same time, can we use the satellite precipitation in that particular model? So achieving this research question, the following objectives are set. Like first, we need to derive the near daily river discharge time series by merging the information retrieved from the multi-mission satellites. Secondly, we need to calibrate the hydrological model like the here we have, for example, we have taken the semi-distributed SWOT model as the reference model, and we use the multi-mission retrieved stream flow information to calibrate this SWOT model. And the third time, to assess the utility of these particular high resolution satellites to calibrate the SWOT model and how it will help us in a data sparse condition. So we have, So we have taken for this analysis, we have taken the eastern basin of Brahmani rivers in India, and this river, an outlet of this river basin, there is a Jason satellite pass is there, and we have taken the water level time series from the Hydrowave website, and this particular basin is a hydrological character for the land use characteristics. This is the agricultural dominant area, and the soil and land use land cover information is provided in the map. So coming to the remote sensing based river discharge estimation. So as we have the CM based approach, which the CM based approach give us the pixel signals in the environment in the environment region, the C by M ratio could be used as a proxy for river discharge estimation as given by Tatnuli et al. 2013. So this particular methodology is being developed for perennial rivers and the we can use it in a medium and large size rivers. But however, but we are now dealing with the narrow rivers or the variable water with tropical rivers. So how we can do that? For that, we need to have high resolution satellite signals at a daily temporal scale. So for that, here the model framework represents that can we use the fusion approach to increase the high resolution framework, like the efficiency of high resolution framework. So for that, we need to have two base pair of images like the MODIS and Landsat at same passing date. And using that images, we can derive you can generate the E*FM model, and using this E*FM model, we can get the synthetic Landsat images like the 30-meter Landsat images at daily temporal scale. And using these Landsat images, we can develop the CFOS model with the integration of Frank copula or a non-parametric function to get the CFOS model. And at the same time, we have the altimeter-based rating curve approach, the classical robust approach, where you can generate the time series by the rating curves. So this is the time series we have generated at the Talcher gauging station of the outlet of the basin. We can, as it is a tropical basin, we can see in the monsoon periods when the altimeters is working very fine, like it's capture the dynamics, and sometimes the altimeter pass is not there. That's why some peaks are missing. So these are the discrete observations. Like the CFOS model is the blue one, the altimeters are the cross one, the red one. So the altimeters is presenting like there are several passages, but it's a discrete observation. And although CFOS model, because of the cloud cover surrounding that area, the CFOS model fails to capture the dynamics. So in that case, how we can, this is a discrete observation. So how we can... At the same time, we have satellite precipitation data, several precipitation data, but we found this four precipitation data is quite related to the IMD observed reference precipitation data, and we have also tested the efficacy of this particular precipitation data first. Then those precipitation data and the static parameters like the land use, DM, and the soil parameters is being used to set up the SWOT calibration. And for this SWOT calibration, we have used the remote sensing derived discrete observation to calibrate this SWOT model. And using this calibration, we have 5 model variants, like with individual precipitation data sets. And using this calibration, we have also validated the SWOT model for 2 years time period. So you can see the spatial variability of the rainfall, and we can clearly see the monsoon, how the monsoon is varying during the month of June to October. It's a quite dominant period of monsoon is showing during the temporal variation is quite drastically changes throughout this year. So you can see from this calibration graph, you can see the SWOT calibration has done only on the basis of discrete observation of the remote sensing. Like when we have the remote sensing observation, the model is calibrated the parameters on that particular, by taking on those particular days. And using those calibration, we have validated the model, and this validation is being a continuous time series. It's an open loop. So we can get the during the validation, only the SWOT model parameters is being transferred so to the validation period, and we can get using those precipitation data sets, we can use the validation, and during the validation, the most of the model is performing quite good, like the NSE and KG greater than 0.5. So third, we are planning to have a data assimilation approach, so how we can get a continuous time series in a data sparse condition. So for that, if we have a remote sensing observation during a particular time period like 2015 to 2017, using that the remote sensing based observation, we can calibrate the SWOT model. At the same time, the continuous observation we can found by the validation of the SWOT model, and then can we integrate the remote sensing based observation during the validation period and the SWOT continuous observation to get a continuous time series in the data sparse condition. So for that, this is the preliminary trial we have made. Like we made 5 model, like giving the percentage to remote sensing and the percentage to SWOT. So in this particular, giving the weightage, we have set up 5 different model, and we found, this is the observation we found, like when the remote sensing based observation is 0.7 and when the SWOT observation is 0.3, when you're combining those observation for deriving a continuous time series, we found the NSE is improved by 0.8 or near about. So this is the continuous time series we have derived for integrating the remote sensing and SWOT with a continuous framework in a data sparse condition, where we can see the NAS efficiency and the KG is quite improved by considering both remote sensing and SWOT in an integrated framework. So coming to the conclusion, the proposed approach using the multi-mission satellite information, we can derive a discrete time series of remote sensing in a near daily time scale, where we can use the multispectral images and as well as the altimeters in a same time frame. And the same time, using those information, we can discrete observation using the remote sensor, we can set up the SWOT model, and at the same time, we can also use the satellite precipitation data sets to calibrate the SWOT model in a data sparse condition. So during the calibration, all the model is performing quite comparable performance compared to the IMD observation, so that we can say we can use the satellite precipitation data sets and the remote sensing in a same frame. So irrespective of the SWOT calibration against the remote sensing discrete time series, the delete simulation at a continuous time scale was reproduced by the SWOT model during validation period with a satisfactory performance with KGE and NSE greater than 0.5. And coming to the last one, we have initially tried the data assimilation approach, and this is quite satisfactory when for a data sparse condition, we can also increase the data assimilation, like enhance the model performance using the advanced data assimilation approach, like the Kalman filters we can also use. At the same time, we can also evaluate the model performances with different model sensitivity parameters, and hydrological diagnostic hydrological evaluation could also be the next step of this particular approach. So coming to the outlook, we need to investigate more regarding the regarding the merging approaches, like how we can merge different satellite information to get the continuous observation from the remote sensing, and model sensitivity and the uncertainty of the hydrological models, and with respect to the model structures or with respect to the model conceptualization should be carried out, so that we can get how the remote sensing based river discharge could be used for the hydrological analysis, and integration of SWOT mission could also be the next objectives for this study. Thank you.
Thank you, Debbie, for this really nice presentation. We have time for a few questions. If someone, yes?
Okay, thanks for this interesting talk.
Thank you.
I have one question. In the conclusion, you mentioned that you will investigate the model sensitivity and uncertainty.
Yeah.
But did you already investigate the parametric?
Yeah, I need to
sensitivity?
test that parametric. Yeah, I have already tested the parameters, and the parameters are within the range. Like the transmissibility parameters, transmissibility is also same within the range. Like we have selected 5 sensitive parameters for the SWOT model, and for different precipitation data sets, those parameters are remain quite same. And we will also do the sensitivity analysis for the parameters.
Okay, and does the various approach allow to better estimate which are the sensitive parameter and in terms of parameter identifiability?
Yes.
Yeah?
Yes, this is working. This is quite working in that page.
Is there more result about this?
I have the results, but we have 15 minutes presentation.
Yeah, but is there any publication coming soon?
Yes, I will try.
Great. Thank you.
More questions? I have one actually.
Yeah.
Sorry. So if I understand well, your best combination of Q remote sensing and Q model is when the majority of discharge comes from remote sensing.
Yeah.
Did you test it to go like 90 and 10%, or did you think that maybe SWOT is
up to 0.7?
Yes.
And up to 0.7, it's working because we have taken several combinations.
Mhm.
But after 0.7, it's quite straight line.
Okay.
So performance.
But SWOT has a really small impact on your discharge. If I understand well.
Yeah, but not small impact. And also when we don't have any remote sensing observations, like multispectral is not there, altimeters is not there, then we can rely on the hydrological model.
Yes. So my point is maybe you could try some simple model, which is maybe, I don't know, discharge model correlation from upstream to downstreams.
Yes.
That may provide the same results than SWOT without having to calibrate it.
Yes, so
Just,
that's why I'm saying for the model structural basis, like the conceptual model and the semi-physically based model, physically based model could also be tested in that same framework.
Thank you.
Thank you.
Okay, so yeah, I think we would. Thank you very much.
So we can shift to the third presentation from you.
Yes.
Okay. So you have a maximum 20 minutes. We're slightly ahead of time, so.
As the mouse. So I will present today the work which is that Romulo, a colleague from JET, is doing in the frame of a CCC project, which is for investigating the impact of climate change on the water cycle. And we will focus today on the satellite-based hydrological modeling of the Niger Basin and look at the role of different rainfall events on the recent flood that occurred in Niamey in 2020. So we already talked a lot during this conference of the precipitation. We know that it's a vital component for all the compartments of the water cycle, and that it plays a really huge role in extreme events, droughts and floods. We have here an example of images of the impact of the 2020 flood in Niamey. You can see that the river totally transborded from its bed and caused destruction, and people had to leave their home. And unfortunately, it's one of the most uncertain and hard to quantify variables in the water cycle. But on the other side, we have now reached, let's say, a golden age for satellite estimation of rainfall. You can see here that we now have a huge and a really consistent constellation of different kind of satellites that measures different physics and that permit to, by some combinations, to infer rainfall at really short latency timescales. And this short latency is what is many times required for flood analysis and prediction. So there are several techniques for merging the different information from infrared and so on, passive and active microwave infrared. You can use physically based models, you can use statistics and also other more refined approach and more recent, such as AI, for example. What is interesting also is that some of these rainfall products use a network of gauges that are available all over the world. Obviously, like for discharge gauges, the gauges are not evenly distributed on the world, so many of these products work well in locations where there are gauges and less well in other locations, like for example in Africa. So there is a lot of uncertainty in these products, and the uncertainty is not evenly distributed, and it is what is one of the issues in tropical areas. So to look at the impact of rainfall events on the floods and on this 2020 Niamey flood, we use a framework that you already saw yesterday, which is a combination of the MGB hydrological model inside a Python scheduler. So you have here a little view of what the platform looks like. And we built and we calibrated the MGB model all over the Niger Basin against in situ gauges, and it was also validated against radar altimetry. And in this framework, we can input several precipitation data sets. So here you have just an illustration of what is the impact of the different rainfall data set and their uncertainty in the discharge. So this framework, it can help understanding how does the uncertainty in rainfall propagates in terms of discharge and from upstream to downstream. So the test we did in the Niamey region is because the rainfall and the discharge there is really complicated, and is composed of two main components. The first one is the rainfall that falls in the Guinean region, which is here in you don't see my mouse, right? Al pointer. Yes, sorry. So you can see here that this region contributes for the discharge in Niamey, which is here, but it contributes for the discharge in Niamey few months after the rainfall, because it passes through the Niger inner delta here, which is a really flat area where a lot of evaporation occurs. Just remember, here is the Sahara Desert, so there is a lot of evaporation, and this blue area creates this slow hydrograph, which is the black or white flood, depending on who speaks. Now, this little area here, and what's the precipitation on this little area contributes to this red flood, which is the so-called red flood. It is called red flood because it's a lot of laterite, so the flows are really red when it occurs. And you can see that on some years, and recently since 2000 year, there has been a lot of really severe floods and really fast floods, because it's almost flash floods in this region, so it's really hard to predict. Now, for 2020 flood, you can see that there is a big difference, for example, between the two last severe floods, which are 2020 and 2012. You can see here in blue the 2020 flood, and in red the 2012. And the 2020 flood was really critical. And here we just show that there was a standard deviation during the DGAs, so June, July, August period. there was a standard deviation of more than 1,000 cumex in 2020. So now we did several experiments to try to understand how does the uncertainty play a role in this flood. So first we perturbated the rainfall in the upper region. So we tried reducing by half and increasing by half the precipitation in this area. So we did a lot of simulations between this range, and you can see that changes that it has a great impact on discharge. And you can see here the gray area, but not too much on, as expected, on the red flood. Even if you have a bigger volume coming from upstream, the red flood will be impacted. Now you can see in this test here where we only change the participation on the red area, that the same range of perturbation can cause really huge impact on the flood of this region, and almost no impact on the rest of the hydrograph. The question now that we try to understand is what kind of event plays a major role, and you can see here that it's a picture, an animation of the total rain. And you can see that the major events are caused by MCS, which are mesoscale events. So we did a decomposition of the rainfall between what is not MCS and what is MCS, and you can see that here if you withdraw the MCS. So the main one, if you withdraw only the main one from your rainfall, you already decrease the flood by this quantity. And if you withdraw the 10 main precipitation systems, you see that you're in a situation where no flood occurs. So as a conclusion, we saw that in several basins, the precipitation is the main entry to the hydrological system, and it's highly variable in space and time, and mainly also a lot in the tropics. And the lack of in-situ measurement is really an issue in these areas. And to measure this flux is really complex because it involves not only two-dimension processes, but also three-dimension in the clouds. So they are really hard to estimate. However, with the recent advances, with the first TRMM and now the GPM missions, we have reached in these precipitation products quality and resolution that turns possible using them for hydrological applications. The few messages that I could send is that the short latency of these products is really critical and can effectively be used for flood analysis and prediction. But before that, we have to understand what are the uncertainties that lie in these products. And it is really important because it varies a lot regionally. And the mesoscale convective systems that we analyze here in the case of Niamey and the Niger basins are really the drivers of the hydrological cycle, even if other events can have a role. But understanding how they could change in the future is really important for this kind of analysis. Last slide. I think that there is still a gap to bridge. And this is us here. We have to merge meteo-satellite communities that normally stop when the product is released. So the hydro community that many times doesn't understand the uncertainty that are inside the products. And really this understanding is critical. The other message is that we have now a large bench of products, different products. We saw today precipitation by satellite, but you can use cellular networks to estimate precipitation. You can use radar information. There are a lot of radars all over the world. And the idea is that we have to merge all these different measurements to improve the quality of the global data sets. and improve the quality both globally and locally. And the last, which is less fun, but still something to say, is that we have to understand the cloud rain systems and their physics inside to help understanding why there are this uncertainty in these products and how the uncertainty can propagate inside watersheds. That's all. Thank you.
Okay, thank you, Adrien. So we have some time for questions. Or maybe Adrien, you have a question for yourself. No, no question. I can ask one. One question? No, okay. Yeah, maybe I have one question. I have maybe two questions. When you have this type of tools, and the idea is to provide information for people that can be impacted by these flooding events. And at the beginning, some slide you said it was a pre-operational tool. And my question is how it can be used in operational conditions. How long it takes from the time you have the data until you have some valuable information that you can provide to the people, and who is doing this job? Is it fully automatically? Is it some consultant companies or some companies making this work to give the information to the people? So in terms of operational tool, how you see this can be included into a operational chain?
Thank you for the question. Yes, actually, we call it pre-operational because there are still a lot of research to be done that has to be done in laboratories. But I think that we already have this platform deployed, and the point is that we already shown that it can be used in real time by the basin agencies, for example. The fact is that this kind of approach where we test several precipitation products and so on can also help to understand where does the uncertainty come from, because obviously there is uncertainty in the simulation, and you can check on the platform today and compare with in situ discharge, there is uncertainty. But if we manage to understand where does the uncertainty comes from, I think we could bridge this gap this time between the operators that need the information and the information producers that in this case is research labs. Sure.
And the time step of the model is like what?
No, it's daily.
Daily. Okay.
But obviously, for this kind of fast flood events, we should investigate at least 3 early simulations. And what is interesting is that these precipitations products, they have several accumulations period. They exist, most of them exist on early time step or 3 early time step. So this is one of the next steps to that we will put in work.
Thank you. Other question? Yeah, there is one question.
No, it's just toward your question. I said for such kind of product, I'm not sure we have to wait that the science is perfect. But when we deployed such kind of models, we also learning by doing, and we can do some recs on the event. And if you have the system already deployed, it's better to improve it and not to wait. So I think it's also, and when you a client asks for, of course, you don't want to wait for many years. So learning by doing is only a way. It's a way to improve. Yes.
Yeah, I agree. We still have time for questions. Don't be shy. Yeah, Simon.
Yeah, thank you for the presentation. Do you have any idea of the quality of the available weather forecasts of this region? I don't know if there are some very specific forecasting systems over this specific region. And I know also that the African monsoon is a very complex system, hard to forecast. But for instance, the ECMWF forecast, are they useful to try to forecast this kind of flood events?
Yeah, thank you for the question. I don't know the quality of the forecast. I think that Meteo France has a dedicated product for Sahel zone, if I'm not wrong. But anyway, the question, yes, it's hard to predict, hard to forecast. But as you saw, the most important events in this area are the mesoscale, the MCS. So we are investigating methods using a bunch of observation and artificial intelligence to try to reach this short-term forecast, at least 1 to 3 days. That could be really helpful in this case. So I cannot say about the quality, but obviously merging this kind of forecast with UCMWF forecast and so on could be, I think, a great asset for short-term prediction.
Yes, thank you. Okay, I have another question. Maybe I am wrong, but I tried what I will present after that. I tried to work on the Niger, and from what it was not working. And one of the explanation is that some zones are very flat. And I was thinking, but maybe I am wrong, that if you're interested by flood extent and this type of stuff, hydraulics model are maybe better than hydrological models, but maybe I am wrong. So can you, because here you are using a pure hydrological model, and still you can have a good prediction of the flood extent, and or do you think that some hydraulic, like 2D models or simplified models, can be also interesting, or can you do the job just with a hydrological model?
So yes, in the case of the Niger Basin, it was a Brazilian colleague of us that developed a special module inside MGB, which was an improved version of the hydrodynamics inside the model, which was, let's say, 1.5D. Because, as you said, there is this really flat area, huge and flat, which is inner delta, and obviously hydraulic, fine hydraulic model would work better in this specific area. And what would be really the best would be to include this kind of hydraulics locally, and on the what you saw, the smooth part of the basin, you can use hydrology and hydrodynamics more classics. But the problem in the inner delta is that it is so flat that even observation from space won't manage for now. I think you won't allow you to catch all the possible divergence of the flow.
Okay, thank you.
Thank you.
So we can shift to the next presentation with mine.
Yes, so you have 20 minutes.
In fact, there is a bug on the program. The title for my presentation is the same as the second one, but so this is my presentation. So the title, and even I changed a little the title, so it's a river discharge estimation from satellite observation, and the original title was application on the Congo River, but in fact I applied this methodology on other rivers, so I can say it's a global application, at least for some type of rivers. And even recently, the last one I used was on the Ganga River. So I am not presenting algorithm based on the SWOT discharge algorithm, so I hope you will not be too disappointed. But I will make some links sometimes on how SWOT can be used in this type of work, or how this type of work could be used also in the SWOT context. So I present this on behalf also on my co-author indicated here. And this work was done in the context of a collaboration around the CICOS institution, which is Commission Internationale du Bassin Congo-Ubangi-Sangha, with different partners also indicated here. And the idea of this collaboration was to use satellite data for rivers. At that time, it started, I don't know, like maybe 5 years ago. And so at that time, of course, what didn't exist. So the idea was to use first classical missions, and then also to prepare some future work for the SWOT mission. And as a preliminary remark, we got the seed questions that were discussed 2 years ago. And when I looked at these seed questions, some were ringing a bell with respect to what I am going to present. One of these seed question was how you go from spatial information to flow discharge. So here I will present one approach using simple rating curves in order to have some operational easy applications. Also using some modeling, so I will show what type of modeling. And it was indicated that it necessitates rainfall data, which is not exactly true in my case, but somehow I will show how. And the second seed question was also how to alleviate from the space, the coarse resolution in both space and time using modeling. And so also I will illustrate this. And some other questions were also interesting, but it will be more investigated with other work. And for example, for river cross section, also we have some work from ESA-ESRIN with a poster number 73 on this topic. So what do satellite observe? So okay, I will just spend 2 seconds on this. You already know. And with SWOT measuring both elevation and water extent, we had some presentation interesting yesterday morning. And what they don't measure discharge, even though SWOT, sometimes you can read that SWOT will observe discharge. No, discharge will be estimated. And we are working at the moment inside the science team about this discharge algorithm using 6 algorithms, 2 French and 4 American ones. So at the moment we are running this on some basin watersheds, and it will be. I had some question about that. It will be available the official discharge product by end of 2024. But some presentation of the Calval period will be presented. So in the meantime, waiting for that, the idea during this work was to use existing satellites. So we have seen during these days different approaches, some data-driven based, some based on hydrological approaches, like the one presented by Adrien or also Simon, using different type of hydrological models and using rains in these cases. And then what I will present here is a different one using, in fact, hydraulics models. So in this case, we don't need explicitly rain. So the idea at the end, in order to be operational, is to have, in fact, rating curves, so that after you have this rating curve, which is very classical, but there are different ways to generate these rating curves. Then when you have water surface elevation in real time, using this rating curve, you can get the discharge at different locations. So here I will generate this rating curve with by a hydraulic model. So the question is here, how I generate this hydraulic model, which is a full Savenant 1.5D hydraulic model, using only existing information, existing satellite or global database. And then to assess the quality of this model and to point also the limitations. So what I do here, I will illustrate this on the Congo Basin on 1,800 kilometers of the Congo River, and also I have some slides, but I don't think I will have time to show them about the Ubangi and Ubangi River, which is one tributary of this Congo River. And on this one, yeah, okay, as usual, we had very little in situ gauging stations. only 2 on the Congo, Malakou Tresho, and 1 on Kinshasa. I will use the one on Kinshasa. And there is only one on the Ubangi, at least the only one I had access to. Maybe some more have been installed recently in the context of some projects, but I didn't have access to this data. And the first global database I am using is a global with database large river from Yamazaki. So you have access to this. Its resolution is 18 seconds. And also, compared to what I presented on this methodology 1 year ago in Montpellier, I am using now Hydromerit at 3 seconds. The advantage is it corrects the elevation errors compared to this version. And in this database, so it's a global database. You have lots of rivers. Here I use width, and it comes from SRTM and corrected SRTM from Hydromerit. So I use the width, water surface elevation, flow direction, and flow accumulation. And since it's based on SRTM, this information was taken from this period in February 2000. So this database is really very nice, very few bugs, and so it's the first type of data I use. The second one is a water balance model. And also water balance model, so it's a global hydrological model with this. So you have different type of data in this database. You have the average discharge from this period. You can also have quantiles. And okay, so the resolution is larger. So it's 20 times the one of this global width database river. And for information, in fact, in the SWOT discharge algorithm, we also have access to this database. So it's some in the official discharge product. We have access to 2 type of average discharge and quantiles. This one and also the one from grades. So since we have a difference in the resolution between the 2 databases, I had to make some adjustments on the location of the tributaries. So I have some automatic algorithms that do that. All that I show you is entirely automatic. On a new river, it takes about 2 minutes to do this. Just giving the geolocation upstream and downstream of the river we're interested in. So here I have to make a correction for the location of the tributary. So the initial location, so it's a longitudinal profile on the 1,800 kilometers of the Congo River. And here you have the original water balance model mean discharge here. And then by using the flow accumulation area that is in a Hydromerit, then I can shift the location of the tributaries. So it's the red line. And then I make a second correction. Since here I have an in-situ station, I make also a correction of this, in fact, discharge profile, depending on the timing of observation during SRTM. So I make a correction, I'd say, in space and in time. So here, with this information, then I have a longitudinal profile of the discharge, and using this, I have a longitudinal profile of water surface elevation. And okay, so this is a rating curve at Kinshasa, and it's the one I use as a downstream boundary condition of my model, hydraulic model here. And for the Ubangi, the in-situ station is in the middle. So it's very interesting what I get on Ubangi because it's a different context. And then I use something very simple, which is also the equation we use, in fact, in the operational product to provide for SWOT, to provide the discharge, modify the Manning-Strickle equation, modified because here we use a water slope instead of the head slope. And then I invert this equation, in fact, to compute what is missing for my model is the bed level. So here in black is the bed level that I get just by inversing this equation. So for example, here you can see that in the Malebo pool, we have like 20 to 30 meters depth, according to what I get. And also since sometimes you can have drops, also I have an automatic introduction of wheels at drops depending on the fluid number, for example, or height of drops. So then I have enough information, in fact, to make a hydraulic model. So at this stage, I have automatically an hydraulic model that can run in on the computer, which is a thick. It's a hydraulic model based on some equations that we developed in my team. So then I get the virtual stations. So here I got an extraction recently. So to extract this virtual station information, water surface elevation, okay, I do it manually on Hydroweb, but also it can be automatized. And here I got, so now there are more virtual stations than 1 year ago. There are, okay, 27 old ones in green here. 2 JSON2 here, and then all these one are either Sentinel-3 or 6 or JSON3, I guess. So in total, I have 98, which is quite nice, quite a lot. And if I take only the recent one, still active, it's 69 plus the in situ one. So using this virtual station, I have the locations where I am interested in designing a rating curve, and then I do it automatically with the hydraulic model. So then I have 2 ways to generate this rating curve. Either I generate, using the hydraulic model, a series of steady state calculation with different discharges. And for each discharge, I get an elevation, and then I can get the corresponding rating curve. So it is a green line we have. Oops, sorry, the green lines we have here. And also I can run an unsteady state simulation. It is a red line here, and then you can see that we have some hysteresis phenomenon, okay, which occur where we have backwater effects. And then recently, also in Hydroweb, so I discovered that when I downloaded the latest data, there are some rating curves information which comes from Adria, so generated with a very different methodology using MGB, and so purely hydrological model. And then I was very interested to compare what I was getting. So every time there is this rating curve in virtual station in Hydroweb, so I generate also automatically. So it's these dotted black lines where I have the corresponding rating curve. And then sometimes they are quite close, but still some offset sometimes. And here, this one, which is the second after upstream of Kinshasa. So of course, on Kinshasa, I fit very well the in situ because it's my boundary condition. So it's good. So here I was surprised or interested at least to see why there was a difference. So it's the one at kilometers 755. So there was quite a difference between the two. So then if you use water elevation inside the rating curve, so this is a difference between the one from Adrien, that is in Hydroweb, and the one I get with the methodology I presented before. So you see mine is overestimating the peaks, and I think yeah, I am overestimating it. And the difference is about 20%. If I take the peak here, I have an overestimation of 20%. So I will discussion with Adrien, maybe he's underestimating, we don't know exactly. But then I had a look at the location of this rating curve. So this is here the bed level I compute with my methodology. Here the blue line is SRTM elevation, the original one, and here the green one is the one from Hydromerit. And we see we have some jumps here, but it's more an artifact of the probably of the Hydromerit. But I was wondering if we had some real big slope at this location. And also here we have 2 virtual stations, in fact, one at 574. So I don't know exactly the reason, and with some differences in the elevation. So maybe there is a problem of data here, maybe it's just a problem of the methodology, but it is certainly a location where I have to clarify why I have a difference. And I think a better explanation also is probably because when you look at how the difference between the two is probably I underestimate the friction. And in this location, it's not very true, but on the Congo River, it's a braided river. So, and here I have a unique bed. So if you have a braided river, of course you have more friction because you have more weighted perimeter. So I will try to work in this direction, and it will go certainly in the good direction, but it's still something I want to do. Before this rating curve, in fact, which are very recent, the only way to validate my methodology was to use the information I had access to. And on the Bangui, there is one interesting rating curve at Bangui. And I was very surprised I could get a very good fitting. I had a 3% relative RMSE at Bangui. So, okay, I was satisfied, in fact, by this. Then the other measurements, I had 2 ADCP measurements close to Kinshasa, in fact. So I don't know if it is the one that you took. It was in 2015. So then I could compare because my methodology, I compute a bed level, so wet bathymetry. On the two, I could see that, okay, the fitting was quite good. The largest difference was for the weighted area here. So it was the second way to validate more or less the wet bathymetry I was computing. There were some measurements, ADCP measurements, but I didn't have access to this data at the moment. But if it's available, I will be interested to see that. And then the third way of validating what I got was to check the velocity wave, the wave propagation time over this part of the Congo. So I had 2 ways to compute it. I will show a few slides on that. And using the satellite observation purely, I got this velocity. And from my model, I was very surprised, but I was very close. So I think I was very lucky. I didn't dare to do this calculation again, but at least in terms of range, I was okay, very satisfied. So these are the 2 ADCP, 2 minutes. Oh, ADCP measurements. Okay, I gave already the figures here. And for the velocity, okay, so then if you have this is altimetry observations, and you can see some waves propagating downstreams. So here, this is a zoom. I do, okay, sometimes it's only one observation in 27 days. So I do some spin interpolation to get the peaks. And then I do some fitting, least square fitting, and I get the velocity from this. So you see you have lots of approximations, but in terms of velocity, okay, at least the matching is good. So I was impressed by that. Okay, I don't show the Ubangi, but this is the rating curve are probably closer. And then at the end, we have a sort of prototype. It's accessible on the web. I didn't update this using the latest rating curve I computed, but I will do. At the time, I had only 46. Now I have 79. So I will. But you can go here. You can click on the virtual session, and then you have these graphics. So every time you have a new, and this is done automatically with it gets the elevation on HydroWeb and compute the discharge. So I was afraid to promote this too much because if it's wrong, it can have some consequences for people and maybe for me. But okay, and there are some interesting side products like with the model you can compute these velocities. I had discussion with Cedric, so also it can be side products of this type of models. And yeah, okay, I don't go into details. So as a conclusion, it's very basic methodology. I think it will be obsolete with SWOT, or I hope it will be obsolete with SWOT. But okay, okay. So it's automatic. It's completely automatic. It's very fast. I just need this type of information. Okay, it's a generic approach, but it's limited to large river, or at least to the rivers where I get this information global with. But also now I can use a SWOT database, which has the same type of information and even more information. So also I would like to test if we use a SWOT database. Okay, that will be fully further checked. And also it can be On the other way, since we generate a hydraulic model, also it can be used as a background for data assimilation using other type of satellite observation like SWOT. Okay, I stop here.
Thank you, Pierre-Olivier. Bon, we don't have time for questions, but keep your questions, please, for the discussion. We now meet, yes, Koshlendra, please. We'll talk about a novel framework for the assimilation of SWOT altimetry in a C-trip IDAS model for improving global scale discharge estimate.
It's a PD. Screen. It's a PDF. How you put it full screen?
C'est un PDF.
Ouais. C'est ça, non?
Ouais. C'est mirror.
Just. Yeah.
C'est du lourd.
C'est un PDF, donc t'avais pas le...
Screen by Control L. Control L. Find the name.
So thank you. So I'm going to actually present the culmination of dedicated efforts, which has been made by several years in the CNRM at Météo France, especially headed by Simon Meunier. So I would like to just to thank us the team of Simon Meunier, Aaron Bon, and Patrick at the CNRM. So this is actually the long-term project for many years dedicated, done for the idea of integrating SWOT into larger scale hydrological models in terms of assimilation. So I joined this team 8 months ago in CNES postdoctoral fellowship. So coming to in the context of large scale hydrological modeling system. So the idea always been to use this large scale hydrological modeling is to monitor and forecast the continental water cycle dynamics. And this is very crucial for the purposes like agriculture, risk management, energy production, and adaptation to the climate change. And to having this monitoring system requires a very good understanding of hydrological processes, so such as storage. So of course, the water stored in the reservoir, lakes, and rivers and aquifer. And also the fluxes, which are the energy exchange with the atmosphere and also with the ocean in the closed system. So for this monitoring, we of course require the observations. So this comes from mainly two places. One is like local scale, we can use the in situ observations. But when we go for the large scale, of course, we need the remote sensing satellite observation at the basin scale. And at the end, of course, we use the modeling, having an edge of to represent the continuous representation of river discharge in space and time, and also to anticipate that short term and long terms. So how we do it at CNRM, basically we represent the water cycle, continental water cycle by using basically two models. So one is like a ISBA, which is a land atmospheric model, and the C-trip, which is river routing model. So the hydrological model, actually, we use ISBA to understand the processes and the interaction to generate the past analysis and climate projection also. So the ISBA actually computes the vertical exchange of energy with the atmosphere in terms of the evaporation and transpiration mainly. And of course, ISBA also computes the drainage and runoff, which is the feeding to the river routing model C-trip, which computes finally the river discharge. So this is the whole framework of ISBA and C-trip modeling system. So coming to the data simulation, as I told, the Meteor France actually it's working quite a long time for generating a lot of data simulation tools. Previously also to improve the reconstruction of the past water cycle dynamics and quasi real-time monitoring of water resource and short-term forecasting. And the idea was always been to integrate the observations into the model in spatial and temporal scale, and keeping in mind the consistent consideration of uncertainties in the model and observations. And in almost last 1 decade, the CTRIP HIDAS, which is the hydrological data simulation system for CTRIP, the idea was to include the satellite observation like nadir altimetry, which had previously shown its performance in the large scale basin like Amazon, and the current work which we are mainly focusing on in perspective of the SWOT mission, like how we can integrate the SWOT observation in this large scale data simulation system. So, of course, we heard quite a lot about the applicability of SWOT missions, so which can monitor the rivers wider than 100 meters, of course, with some quite nice results. So here we did a lot of tests, and then one of the tests is showing here for the Congo basins. So the red line actually represents the rivers which has been monitored by the SWOT in one cycle in 21 day repeat. And the different colors actually represents that how many times the SWOT has observed this basin. So of course we can see the blue line, like we have at least one observation almost everywhere in the basin, and we have more often 2 observation, and also sometimes we can get 3 observation in 1 day repeat orbits. So of course we have the nice spatial coverage, but we have some inconsistency in temporal scale, so which can lead to some underestimation and overestimation. So that's why we not only want to use the SWOT for just for monitoring, but also to use into a data simulation framework to have a continuous time series in a spatial and temporal scale. So how we are doing it? So we are using kind of a twin experiment. So first we are, of course, we don't have SWOT in level 3 data yet to ingest, but we are using the proxy SWOT data. So first we are using the realistic SWOT orbit using SWOT logical hardware simulator. And then once we have it, we run the first simulation, which we consider as a true run. And then we add a realistic noise into that up to 10%, and we did a lot of tests with different uncertainties, but here is a 10%, and then we assimilate what we just simulated. So here we are using the ensemble Kalman filter, in which we are perturbing the atmospheric forcing, and then we are assimilating. But the main here is to emphasize is to the use of Kalman filter. So here we are using the local ensemble transform Kalman smoother, and we are also using the latest version of CTRIP, which is 12D, which is the 1/12 spatial resolution, which is quite more compatible with the SWOT resolution, which we are going to get in level 3 maybe. And then we are simulating the SWOT derived discharge, and also the physical based localization techniques to reduce the spatial random errors. So I'm going to emphasize more on like a physical based localization. Why? Because in the classical way of using localization technique is the first one, the left one, we can see the based on the geographical distance, which is classical being used in meteorology and oceanography. And then the right hand side shows, which is more to hydrology part. So it is like based on the distance within the river network, and this localization works more well with the river networks. But here is one issue, like we have one red dot and one blue dot, which shows that there could be one observation somewhere in the, not in the mainstream, but in the tributaries, which going to especially impact the whole domain, and which we don't want to update it. So we have explored more, and we found out by the paper Menikareval et al. 2019, in which he had used the localization based on the hydrodynamic distance. So in this localization technique, we check each pixels, and based on the dynamic flow between in both the pixels, and also what is the correlation between the time series and the difference, we update pixel by pixel, and we compute semi-variogram, and then when we look into the different points in the mainstream and in the tributaries, we get some interesting results if we do the localization based on this covariances. So here are one of the results in which at one point to see that how the localization is going to impact the river discharge. So from top to bottom, it is like we have used the covariances at the end, and we can see, of course, here we have used a different model, MGB, as a true reference, and then we try to check that how much localization is going to impact. So we have improved a lot the RMSE and also increased the efficiency. So we have introduced or included this kind of localization technique in ensemble command filter and data simulation framework. So before going to the global scale assimilation system, we divided, the entire domain distribution for running the global scale assimilation. So we have used this merit, Pathsetter level 2 basins, and by Lin et al. And Yamazaki. So in this, they have divided the entire globe into this 61 smaller zones, and like each zone has its unique code. So for now and for results, I will be more focusing on the South America. So for the results here, I'm going to show the results. So of course, there's a Pathsetter course 62, which almost covers the almost entire Amazon basins. And the right-hand side is the main tributaries and also mainstream and the other tributaries as well. So for the first cycle of assimilation here, January 1, 2021. So the blue color actually represents where the data assimilation framework is performing well, and the red color represents where just the open loop is performing well. And we can see the two vertical patches actually represents the SWAT of the SWAT mission, and then we can see that our framework is not only improving the framework is not only improving the discharge just at the overlap of the SWAT, but also at the upstream side and the downstream side. And when we move to the next cycle, the day 2, and then it still holds not only the current, of course, the previous simulations to be good, working the data simulation framework well. And then when we move forward, so now this is like day 11, which is just the half of the one cycle of 21 days, which is just 11 days. And we can see it covers almost most of the major river basin and also the smaller tributaries as well. Of course, we have some red lines. I will just tell you what could be the potential reason. But in summary, as a conclusion, that our framework is working quite well not only at the continental scale, but at the global scale. We are quite ready for running the data simulation framework at the global scale. So here is the mean AI of the 1 year simulations, and we can see we cover almost most of the major rivers and the minor tributaries as well. But we have some red lines here, even in these tributaries, and one of the potential regions could be the better, even more including the representation of reservoirs and lakes into it, because so far we didn't do it here. So in this context, actually, at Meteor France, the surface team already developed 2 such kind of models, and they have also tested in the local scale, like in Spain. And they found out that when they introduce these models or integrate it in the simulation framework, it performs quite well, even though having the inconsistency of data records of sort, temporal sampling, but still it's performed well. So that is the plan, to integrate it into a current version of ESA-ESRIN C-trip in a large scale, like the global scale. So of course, it's going to improve our simulation even much more. So I didn't make a separate slide for recommendations. The only one is that as soon as we get the discharge river products to assimilate, we can go and test and then provide further recommendations. So just awaiting the coming soon global scale C-trip. Hydras would be the first to having the discharge the daily time step at the global scale. So yeah, just awaiting and for that. So thank you for your attention.
Okay, thank you very much, Coach. We have time for questions. Yes, please.
Nice presentation. So I have a question, it's just by curiosity. Your localization method is time variant? Or it's just, okay. And did you measure it? How much did it improve your simulations?
Like quantitatively, of course, like we did several tests before to check how much length we can encounter, like how far we can go at the upstream side and downstream side, choosing different values of the localization length also, then how it is going to impact. And then we come down to 0.6 as a length of yes, so we did a lot of tests to come up with the 1 point, yes.
Okay. Thank you.
Yeah. And about the localization, if I understood correctly, it was slide 7 or 8. If I understood correctly, in fact, so you're looking at the distance, not classically as you do, but along the network.
Yeah, it is along the river
Yeah.
network,
But
but
then-
pixel by pixel it's moved. Yeah.
But then I understood to know this distance, in fact, you find a correlation in discharge. Is what you do.
Yes.
But why you? Because you have the distance along the network. So why you don't use explicitly the distance along the network? I don't know if my question makes sense, Simon. In the source database, for example, you have this. Or...
Yeah, using only the distance would be the localization techniques, which was in the right-hand side of one previous slide. But in this case, you may have situations where you have, for instance, an observations on a small tributary. And if you say, okay, I want to go down to, let's say, 10 pixels, which could be 100 kilometers, for instance, you will use these observations to correct the discharge over the main river, which is not always a good idea if those 2 points are really decorrelated. So this is why we use this technique, and we call that more like a hydrodynamic distance.
Okay, it makes sense. Thank you.
I have also one question. When you show your map of improvement or decrease in quality of your run, what do you compare your assimilated run with?
With the true run, actually, the indicator is assimilation index.
Okay, so you have your true run, you perturbate it,
Yeah.
then you assimilate.
Yeah.
Okay.
Yes.
Hi, thank you for the very nice presentation. Maybe I missed that, but from where your observation come from? What do you use to generate your observations?
Yes. So of course we don't have solid observation yet. So what we do is first we run the ISBA and C-trip. So we have one true run, and then we put up the forcings, and also for generating observation we include error in it. So we actually are assimilating what we just simulated.
Okay, thanks.
Okay, thank you again.
Thank you.
Okay, so now we have 20 minutes to work for Jérôme on the seed questions. So we prepared some slides. So we are very interested, of course, for your inputs. So when we had the list of the questions of 2021, there are like 3 pages of this on this topic of models, use of models, to be synthetic. So we didn't take again all these 2 or 3 pages of questions, but so we focus on maybe 4 questions at least to start the discussion. So maybe we can start by explaining the discussion. So Adrien will do that for 2. I will do that for 2. And then, or maybe if you can start, if you want to start from other seed question you have, also we can do this way. So if somebody want to start, you can do that, or we will start by some question we can suggest to the audience. Yeah, okay, please do. Yes, yes, of course.
If you have some,
Yeah, sure. Yeah.
go on.
Perhaps it's linked with the first point. So I have questions for your very interesting presentation. I see your area of studies is a square. Did you think for the future, for example, to work at a catchment watershed area? Because, for example, you work with in situ data, but I don't really understand if it was rain gauges or snow measurement. But you can work also with hydrometric data. For example, I make a study recently where snow was a major things to explain discharge in the basin. And the first things was we rejected the sum of rain product because the rain was less than the discharge measure in terms of millimeters, so we can pull out some rain products. At least only 2 products of rain were superior to the discharge. So I can say if you work also perhaps on a catchment area, you can also include hydrometric in situ data. So, well, is it? It's an idea.
Yeah, sure. Yeah.
Okay, so regarding the study on a basin scale, we do already do it. I just have presented these squared areas, but we usually divide the domain in some square areas because it's simpler from a computational point of view, but of course we do work on a basin scale. Regarding the simulation of the data, we use snow gauges because we basically want to match the snow. So we use the temperature to correct the phase. And then also, well, we use also rain gauges because, as I said, we consider also the total precipitation. So we use both. We use both. And the problem relating the in situ data is that sometimes they are not so good. There are a lot of local scale effect. If some sensors are put in a very narrow valley, could be always in a shadow, so the temperature is always lower than the other one nearby. But of course, the physical model need to have a data set that is consistent. Sometimes you have the case with, let's say, 10 centimeters of snowfall at 1,000 kilometers in elevation, and then over a ridge, when you expect to have 20, for example, you have just 5 because of the wind. So the assimilation must be done having a look at the data because they must be consistent with themselves. And this is the hard part. That's why I didn't do it and I just calculated the metrics because it's a hard work to select the correct data.
Thanks, Damien and Federico. I think the underlying question, it's related to the first point we put here, is how do we use the data that we have? Like traditionally, we see the Earth observation data as an input, or we use them for calibration. But we saw on the case of the snow, on the other case that we saw today, that we could use better local physical models, for example, to learn about what is the uncertainty in the data and maybe to expand this knowledge on parts where we don't have in situ. I think I saw your presentation, really nice local information, and then maybe you could improve the global Earth observation data set using what you learn locally.
Yes, as also said by Jean-Christophe yesterday, so, yeah, the idea is to collect as much data as we can and integrate them. So it's not a fight between EO and in situ data also for hydrology. The idea is to take advantage of the potentiality of the data that we can have, so they can be used both as an input as well as a benchmark. So I think this could be the best strategy.
Yeah, I agree. And okay, for snow, it's what you show, and for liquid water, it's also the type. We have many ways to combine data, satellite in situ data, satellite observation models, and in the different presentation, people are using different combinations. And what is okay? I don't think there is one best, but what are the different combinations and how to? I don't know if you will converse towards some best methodology, but for me, it's a important question. And then also when you made your presentation on snow, also I was thinking, and then it goes to the top bottom left questions about timing, because I think we had questions a few days before, yesterday or 2 days ago, on for hydrology or hydraulic, or what or in general what type of information we would like, and we had some sort of agreement that daily observation would be interesting, but also because the dynamics for surface water, liquid water, is quite fast, and I suppose that for snow the dynamics is much slower. So maybe what is available in terms of observation, in terms of sampling time, maybe is sufficient. Also, would you like
daily results usually are sufficient for the snow.
Yeah, and so also the time step we are interested in also is probably, maybe I am wrong, different when you are studying snow or liquid water, probably.
Yeah, that's why the satellite data are very useful for the snow monitoring, because of course, even if the revisit time is poor, it's enough. One measurement per week, it's usually enough to correct the data because of the dynamic
Exactly, yeah.
of a snowfall.
Yeah, for a river, it can be different.
Yeah, must be, of course, sub daily at least.
Some other questions, remarks, recommendations?
I have one question about this time and space issue. Maybe for you, Koshenla and Simon, you are doing global, really nice, global assimilation also in a few weeks or months with real SWOT data. But do you think what you think that SWOT data could help you gain in terms of time resolution? Can you go sub-daily with a simulation of a real moment of the SWOT pass? Because we know that it doesn't pass everywhere at midnight or noon. Is it possible at global scale, or for global scale for now, should we stuck at daily and go further with more regional studies?
Well, we do global simulations, and usually we look at our results at the daily time scale. And for simplifications in all the works we did for preparing the assimilation of SWOT observations, we consider that SWOT observations is, as you said, at noon, for instance. Well, we decided still the computations time step is more like 1 hour maximum. So with that, we are able to assimilate the observation at its exact time. So in the same time, in our model is large scale model, and we do not really expect to have very high performances on small rivers, very small rivers, and very fast varying rivers. So I'm not sure that we really that it could be really interesting to go sub-daily for this context. Even though we could try over small basins, we are also working on improving the spatial resolution of the model. And so this question could be more important than.
And another question that also we raised was one of the bottom right in terms of accuracies and communication with final users of these accuracies, and also in the seed question of 2021 also this point was raised, sometimes saying that discharge doesn't speak too much to people, more elevations, but also I think maybe sometimes it can be opposite, but at least in 2 years ago it was written this way. So has anybody some experience about, and when I show this prototype of platform, I was really afraid of providing discharge to people, especially because I was also not, I didn't validate so much my methodology, because it can have some impact. So I think it's maybe more a question for consultant companies and for researchers, but does anybody have some experience on that, or how you can communicate on uncertainties? Because when I had discussion with people from the in Congo, okay, you show a model, you show a depth, and they say, okay, yeah, and how long it takes to go from here to here, and it seems they believe so much in science that they can take this for granted, but it can have also some impact. So has anybody some experience on that issue, and how we have to do that just to provide uncertainty? I guess it's difficult to do more, but for me it's a concern. And we have seen with satellites when you have a water extent or water surface elevation, now you have quite a good. I mean, the uncertainty is usually quite small, I think, especially with more recent missions. And for discharge, we don't know exactly yet what we will get with SWOT. But okay, if you have a 30% error, 40% error on some bias, how you provide this data, and there's a risk you take to do that? No, nobody's afraid.
I'm afraid. I agree with you. But I think, yeah, the best you can do is providing certainty together with the data. And the risk is if you don't provide this uncertainty, you can sort of show discredit on your, as you was afraid for your platform, like, okay, it's not working, it's not the good value, so it doesn't work. It's the same thing for, if you think about, well, as you said, altimetry or surface water. Sometimes if you provide just a time series of radar altimetry with no information on sentences, people could say, oh, it's not the good elevations and it's not working. And then you throw away years of effort to make the data acceptable. So really the uncertainty is a big, for me it's a big importance to provide this. Now, how to communicate about that, I don't know. I don't know, some suggestions? And on HydroWeb, in terms of elevation, you have some uncertainty. I don't know exactly how it's computed, but on the graph I show on HydroWeb, you had some uncertainties. And this uncertainty I show is the one from HydroWeb on the elevation, and then I propagate this into my rating curve. But then it's just part of the uncertainty, because okay, you can propagate an uncertainty, but then okay, just the methodology is generating. If your methodology is bad, and you can propagate something, you will get something, but you have something in between that you don't. So in terms of uncertainty estimation, for me, what is good is to compare to in situ measurements, but then you don't have this at every locations. So even the uncertainty that is indicated in terms of elevation is HydroWeb is just part of the uncertainty. Only part, yeah. Yeah, Simon?
Yeah, about the uncertainty on SWOT discharge. Of course, if you have 40% uncertainty locally, it's hard to communicate with that. But the great advantage of SWOT is that when you have observations, usually you have observations not at one specific point, like for nadir altimetry. You have observations over an entire reach, which is which depends on the width of the swath. And typically, if you aggregate all the discharge product over the observed reach, more or less you can almost remove the random error. So the idea would be not to communicate on one specific location, but maybe try to aggregate all, so in the context of SWOT, all the discharge you have over or under one swath, using, for instance, data assimilation, but there are other possibilities, or maybe even integrate this into a more complete framework with maybe other observations, with maybe. So with that, you will reduce a lot your uncertainty. And the other point is that we have to remind that for discharge, in situ discharge, we never have zero uncertainty. And actually, the in situ discharge, what we call the in situ discharge, if we measure, if we make a real DCP measurement, you could have something very good. Else, if you are simply based on a rating curve that have been maybe set up decades ago, usually we say we have at least 10% error on in situ measurements, and probably often it is really more than that. So we shouldn't be that afraid of the uncertainty we would get from space, I think.
Yeah, I agree. And even we have this presentation from the person using movies on the water surface to get the velocity field, and it showed just depending on how you treat your data, also you can get differences. And just maybe I can explain in the SWOT official discharge project how you are dealing with that. So we have 6 algorithms that run on the platform, which is called the Confluence platform. And then we have also a step that is called the integrator, also that will put some constraints as the tributaries. So by doing that, we will in fact put some more coherence between the discharges that will be computed individually at the reach level. So this integrator will be used in the context of the official discharge product. And also, since we have 6 algorithms running, so all the 6 algorithms will give a different result. So also we will have a consensus algorithm that will be a sort of mix between the 6. So it's not clear already in my head. Maybe Kevin knows more. Probably we will remove some outliers and take a mean of that. So also in the official SWOT product, discharge product, also we will have some post-processing treatment that will hopefully or thankfully reduce this uncertainty. Yeah.
Maybe Jérôme, you have a thought about this question of uncertainty, because now ESA, I think that in all CCI projects and so on requires the end-to-end uncertainty assessment. So what's the point of view of the agency on this question of the uncertainty that should be? What is your recommendation for this question of the uncertainties?
My message is that we cannot survive without uncertainty, and if you want to, show that your result has some value, it has to be accompanied with uncertainty, and it has to be as formal as possible. It has to be deducted from your processing, your algorithms, with formal with some formal uncertainty. In the past, we've published a few papers on uncertainty in the CCI, one by Chris Merchant in the sea level budget closure phase 1, which is, I think, a Bible for producing uncertainties. I think it's in the scientific world, it's mandatory. And ESA can just say, yes, of course it is. I don't have much more to add on this subject. I think it's good science comes with a variable that you want to exploit come with its uncertainty, especially if you need to feed a weighting function when you assimilate with a Kalman filter or a joint or whatever. So yes, needed.
Yeah, I just want to say, sorry, that dealing with uncertainty, we are sure we are obliged to work with it, whatever the place we are, if it is on data acquisition, modeling, or any recommendation for stakeholders. So I guess the better option is we have to combine the effort to reduce the uncertainty on the various parts of the chain that goes from the data acquisition to the estimation of the variables of interest. Then also we have to maybe communicate quite differently, because if we want to give a single value, it will be source of a lot of uncertainty. We do not have this idea. But if we think about robustness of kind of prediction or estimation, we can say, for example, that we are 100% sure that the required value is in a range which is related to one big work, which is related to the epistemic error. I mean, the epistemic error is where we are now, all we know from the data acquisition to the modeling and so on. And then if we merge all this knowledge as just saying that we are pretty sure that we are in this range, it will be much better than just giving one value, and we are not sure in which extent we are pretty robust with this estimation. Just one way to communicate, and also when there is some estimation that are given from many processes, from the acquisition, then going for algorithm or other various methods of data monitoring and so on. The most important thing is to have a clear idea of what is the chain from the acquisition to the final results, so the user can have a clear idea of what he is using. I mean, just one idea.
Okay, thank you very much. If there is no new question, maybe we can. I know.
Just for the how to communicate for accuracy. For example, I see many presentations where you speak about mean average error, but for us, sometimes we don't present errors like that. It's more statistics. So it's the value of 19%, 90% chance to be between these two values. I think it could be it could be a way to communicate, and it's the way sometimes we communicate to the client. We have the mean value expected, but also a range presented like that.
Okay, thank you very much. So maybe we can thank again all the presenters and the audience with the good questions, and we can go to the coffee break. Thank you.
Advances in the use of Earth observation for land surface and hydrological modeling. And in this session, we have 5 presentations. And the first one is done by Kevin Larnier from CE Group. And he will talk about coupled hydraulic modeling and data simulation over the Niger and Maroni rivers using SWOT river products and other Earth observation missions.
Thank you, Simon. So first, I'd like to thank my co-author, Charlotte Emery from CS Group also, Pierre-André Garambois from INRAE Aix-Marseille, and Laetitia Gall and Adrien Paris from Hydromatters, because we did a lot of work on the data preparation for this topic. So thanks to them. So the context first, as you all know, I think we discussed a lot about that. There is a steady decrease of in situ station over the past 3 decades. So it's difficult to have real-time monitoring on some basin. In developed countries, we have done in situ data networks, but in developing countries, we don't have, and the number is decreasing. So there is a strong potential for remote sensing in such country, for instance, in Africa. And we can use the Copernicus Sentinel constellation and the new SWOT mission. So the objectives of the study is to develop an automatic method to set up coupled hydrology hydrodynamic models using fusion of Earth observation open data products and for basin with sparse in situ data. And also to analyze the benefits of assimilating conventional altimetry and SWOT river level 2 products. So first, the big question is, what do we need to set up automatically a coupled hydrological hydrodynamic model? So of course, first we need both models. We need a hydrological model and hydrodynamic model. So here we have 2 models for the study. The hydrological model is the MGB model from APH. And the second one is a full Saint-Venant model in 1 dimension developed at ENSA Toulouse. So with the particular, this model is particularly specific to using Earth observation. And of course, we have the 2 models, but we need to couple them. And how do we couple them? We need to find the interaction between them. So here is schematics. You have the subbasin for the hydrological model in dark polygon, and the blue line are the localization of the segments of the river modeled by the hydrodynamic model. So first, we need to find the location of the interaction, the boundaries between them. And you have 2 different kind of boundaries. First, what you see in purple is the subbasin that are upstream the beginning of one river portion. So we call upstream inflow points. And of course, through the river portion, you also have lateral inflows. So our methodology automatically select those subbasins that enter the domain inside the river portion. So we have developed a tool for that, and it also can be used for a fully distributed model. This is a parenthesis here, and you have a poster dedicated to this aspect. So there's also this methodology that automatically detect inflow points, either upstream or lateral, from the drainage network of a full distributed hydrological model and the river network for the hydrodynamic model. So here is an illustration on the Maroni River Basin in French Guiana. So here you see the subbasins for the MGB model, and in white you have the full river network for the hydrodynamic model. Here you have the illustration of the 12 automatically detected inflow points, upstream inflow points, which are upstream boundary conditions for the hydrodynamic model. And inside the river network, we have a lot of lateral inflow, approximately 200 lateral inflow points for aggregating all the discharge coming from the hydrological model. Another thing that is quite difficult to get when you want to develop a hydrodynamic model is the estimation of the cross-section shapes. So here we also developed a methodology. What we do here is that we use conventional altimetry in combination with water mass computed from optical or radar images. So in this case, we used ICESat 2 altimetry. So we have a lot of virtual stations. So it's dense in space, but it's not dense in time. And we used some water mass computed from Sentinel-1 radar data for the Maroni River by the Extract-TO framework developed at Certit eCube. So I won't go into details in the methodology, but to illustrate what it does, you have here some examples. So from the water mask, using a dedicated algorithm, we compute the river width from the planform of the river cross sections. So this is what you have in the red curve on the left, and we interpolate at the same time location of the altimetric measurements, so the water surface elevation, and we combine them in the effective cross section. So this is what you can see on the right, and because we have uncertainties in both the width and the water surface elevation, we smooth the effective cross section using power law regressions. So this gives you what the shape of the cross section above the lowest measurement. So we also need to get what is unknown. This is the part of the flow area that is below the lowest cross section. So to do that, we use the Manning equation to infer this unknown flow area. And to do that, we first need to filter the signal of water surface elevation. This is what you see on the left side. And to filter it, we use a dedicated filter, which aims at ensuring that all the slopes are negative from upstream to downstream. So it uses wavelet decomposition, and it's sort of zero some of the coefficient until you get hydraulic an average filtered profile. And from that, we use the Manning equation with a first guess of friction coefficient and the mean flow coming from the hydrological model to get the estimation of the riverbed elevation. This is what you see on the bottom right. Of course, what I don't present here is that you always do filtering, because you have uncertainties everywhere. So it's important to filter that at the end as a post-processing. And so once we have that, we want to assimilate some of the EO data. So here we have a complete framework embedded in the DASFlow 1D hydrodynamic software. It's based on 4D data assimilation technique. Our problem to solve is to minimize a cost function, which is the discrepancies between the simulated heights and observed heights. And in our control vector, we have every time series of each inflow boundary point, the bathymetry that we want to correct, the riverbed elevation, and also the parameters for the friction coefficient. And this problem is ill-posed, so we need to precondition using changer variable and covariance matrix to enforce the correlation between different control elements. And also, we build up a tool based on sensitivity analysis to better constrain our methodology. This tool uses an ANOVA to get the relative influence of each of the parameters through time and for each different observation station. So I won't go into detail because it will take time, but it helps. As you can see here, you have different relative sensitivity. So for instance, you can focus on a subset of the control vector for the beginning of the simulation. So you simulate and you correct that. And after that, you can correct other parameters. And in some places, it's really important to do that because if you want to correct all the variables in the same time, you won't have a good solution. Here I will illustrate this methodology on two different cases, the Maroni, as I said, in the French Guiana, and also the Middle Niger basin. So it's downstream the inner delta. And we prepared a lot of different experiments using different data sets. So most of the time it's based on ISAT2 and water mask to set up the model. And after that, we use different kind of data for assimilation. All of these experiments are not finished, so I will present only a few sets of them. The first one, which is the fifth in the list, is the middle Niger. So we used Sentinel-Tri JSON2 to plus water mask from classical NDWI and Otsu thresholding method on Sentinel-2 images, and we assimilate Sentinel-3 and JSON2 data. And on the Maroni, we used ISAT2 and Extracteo water mask to set up the model, and we tried 3 different data sets: ISAT2 plus Sentinel-3 only, then ISAT2 plus Sentinel-3 and 2 in situ stations over the 5 that are in this area, and also very last results, some observation of SWOT nodes during the Calval. So the first illustration here, so it's on the Niger River basin. On this basin, we have 19 virtual stations only. So it's an old experiment. So at that time we didn't have the ISAT2 to get sufficient space resolution, but we tried that, and we only had one valid station for the validation at the downstream, which is the station of Niamey. And here we compared the results between MGB only and our new methodology with the MGB coupled with the DESFlow1D. You can see that overall the results are quite the same, but you can see that using the fully hydrodynamic model helps in the recession periods. For instance, here you can see that using the hydrodynamic model helps to maintain the discharge, to be more precise on the discharge. Newer results. So the experiments on the Maroni. Here we have lots of virtual stations from ISAT to build the model. And also we have 19 virtual stations from Sentinel-3. And we tried experiment using only ISAT2 and Sentinel-3 to assimilate. And the results are quite poor, but it's normal because we have a lot of parameters in our control vectors because we have more at the 200 and almost 250 parameters for the bathymetry and the friction coefficient, and we don't have enough observation to get a good assimilation. So this is normal. So what we decided here is to add 2 in situ stations at the upstream part of our model, and we incorporate this data in the data assimilation dataset, and we validate on the other 2, and we assimilate the height, the water surface elevation, and we validate on the discharge. So, okay, we only added 2 stations, but with a lot of observation in time. So as you can see, it helps really, it improves really the solution, mainly at these 2 stations, because as you can see, we are below 20% of errors for the first 2 stations. And in the downstream station, the results are better than before, but not, well, in terms of accuracy, it's good because it's 21% and 30%, but you can see that we don't have the really good dynamic. So we need to continue our analysis on that. And finally, so this is really rough results. Don't analyze them too much, but it's an experiment to see if we are able to assimilate SWOT observations. So now we have 5,000 nodes, so it's 5,000 so-called virtual stations for the assimilation on a small period during the Calval, so it's half of the Calval. And okay, the results are promising, but what's important here is that we developed all the framework to assimilate them, and mainly you can see on the lower part at the left, we used the same filtering method that we used on ISAT to filter the SWOT observation at the node level, and it helps a lot to get representative surface water profile. So to conclude, here we developed an automatic setup of a coupled hydrological and hydrodynamic model on river network, not only a river portion, but a full river network. We also have an embed framework for data assimilation that relies on 4DVAR, and it's able to estimate and correct multiple inflow times, discharge time series over the network, the roughness parameter, the riverbed elevation, and yeah, like I said, it's working on a full river network, not only on some portions as we did before. And what's also interesting, it's SWOT ready, and the results are promising. Like I said, it's only rough results. The first data that we have, they are not validated, so it's promising, but it's not so accurate now. And the perspective, we need to focus on longer time series, because here we only tried on a few time period, like 3 months or 2 months or half of the Calval. So we want to focus now on longer time series with the help of our colleagues from Hydrometers. We can do that using the whole time series of the MGB simulation. We also want to fuse historical altimetry missions for the assimilation and the preparation of the model. And also, if we want to go any further, we have places in Maroni, for instance, where there are ana-branching or braided rivers. So we can incorporate, using our method, 2-day patches of this area. So it will be a very good model to show off. And of course, we are interested to work on more basins. So if you want to help to have this set up on your basins, please feel free to contact us. And finally, the recommendations. So using coupled hydrological hydrodynamic model over an entire river network, we can propagate some sparse measurements in space and time using the physically based model. So it's really important because we have access to the wave propagation, and we can deal with sparse measurements. And why I say that is that we SWOT data, we won't have a long period, but we will have good snapshot and at very fine scale and over the globe of all the rivers. And so we can set up this kind of model everywhere. And once we have that, we can use less dense measurements, for instance, conventional altimetry, to assimilate and get very good results. So it's a good combination to get something for the future missions that maybe will be at more frequent revisits, but sparse in space. And it's not a problem with that because we have a model to interpolate everywhere. And also, one problem that we faced here is that we had only a few measurements of width and height, and with a lot of uncertainties, especially on the width. So we need to enforce the improvement of our water mask, for instance, or something like that, to reduce the uncertainty and get very good effective cross-section. So, well, like I said, improvement of the water mask, or maybe more measurements of both water mask and height to get a very good estimation of the bathymetry cross-section. Thank you very much.
Thank you, Kevin. We have time for maybe 1 or 2 very quick questions. Yeah.
Can you go to the microphone? Sorry.
Thanks for the nice presentation. I would just like to know how sensitive is the simulation window when correcting the roughness parameter. I mean, you find a lot of sensitivity of the length of your simulation window. I know I saw you.
Sorry.
How sensitive is the length of the assimilation window when correcting the roughness parameter that you show here?
Actually, we have 2 parameters for the roughness. So we have it's like a power law of the depth of the water depth. So they are kind of static in time. So if you it does not depend on your time window. What you will end with is these parameters that are okay with this kind of flow regime. So for instance, if you only optimize during low flow, you won't have parameters that will work on high flow. So if you want to have something that is okay for everything, you need a long time period, sure. But it depends on what you want to do. And in some places, mainly when you have really changing geomorphology of the river, you need also to have different sets of parameters for each different case. You won't be able to have something that will work every time.
Okay, thank you.
Yeah.
Thank you very much.
And our next presenter is Laetitia Gall from Hydrospace. And she will talk about the contribution of daily observations of water surface elevation from SWOT, nadir altimetry, for near real-time monitoring and short-term discharge forecasting in the Maroni River Basin in French Guiana.
More extensive. No, non, c'est ça. Yes.
Bravo.
Merci. Okay, thank you, Kevin, for this nice introduction. So the title is a little bit different from the program, but it's an ongoing work about the contribution of daily water surface elevation data in the near real-time monitoring and short-term discharge forecasting within the Maroni River Basin, so in the French Guiana. So first of all, it's obviously a team effort, so I would like to thank all of my co-authors for their work on it. So the question beyond this title is how to daily observation of water surface elevation improve or could improve the precision of discharge estimation. And beyond this is why this question and how can we answer it? And at the end, what kind of improvement we will see. So first of all, why this question? A little bit of context behind this. I'm pretty sure it's not the first time that you see this picture during this week, but it's fact. We have a decrease of the available discharge data since the last decade. So we need to have more information now, and especially because of the disparity of this data. Added to this decrease of information, you have also an increase of extreme events like floods and droughts, like my colleague Adrien showed you yesterday, especially in French Guiana. Here at the Maroni River, I don't know if I have the, yes. No. Yes. So here it's the Maroni Basin. So this timeline represents each blue point flood during the last 3 years. So it's in French, but I'm pretty sure that you get the idea. There are a lot of flooding during this last year. And since this last month, not only on the Maroni Basin, but also on all the Amazon, we have a very important droughts also. So as you can see, we have a very important big events, very big events like this one. But we have also we are a lot of different type of altimeter. Here it's an example of a river in this region. In black you have the observation, and in green and orange is Sentinel-3 and 3B. And as you can see, with this mission, you can reach this kind of peaks, which represent flooding actually. So, but now we have the opportunity to have mission and constellation with a higher temporal resolution, like SWOT, for example. So now in the same graph, you have in red with the SWOT calval phase, so at 1 day time scale. And you can see that with this kind of information, you can reach this kind of peaks here. So we know that SWOT is really great, but I'm pretty sure that the altimeter could be provided very important and good information also. But we don't have just SWOT. Maybe in the future we can have also access to other type of constellation like SMASH constellation, for example. We could provide also a constellation of 10 small satellites in the same orbit plane. So with 1 day time sampling at each terrestrial station. So we could provide also a very important information to higher temporal scale. So now, how can we answer it to this question? What is the methodology behind it? So a few parts. The first one, it's in situ data. Even we know that altimetry modeling everything is very great, but we always need some in situ data to validate, calibrate. And so we chose this spacing because we have a lot of in situ data. We made since the last few years now a lot of field mission there to provide a lot of in situ information. So here you have, for example, an ADCP in this station here by Pashton, and thanks to this kind of data, we can provide a rating curve at this specific station. And at the end, with also 21 rating curve all over the basins, thanks to Sentinel-3, 3B, and JSON family, we have also, we can provide a lot of discharge time series all over the basin. Another part of the methodology is the automatic physical rotating method. So we used the RRS algorithm that my colleague Malik showed you yesterday also. So if you have any kind of question about it, please ask him. The other part is a model. So we use the MGB model, but Kevin already introduced the physical part of the model. So it's just a physical-based distributed, it's a physical-based distributed hydrological model developed by the IPAGA at Porto Alegre in Brazil. And so we can also provide a lot of discharge data everywhere and at each time step. So it will be very useful for the next part. And the last part of our methodology, of course, is the assimilation. So we use an approach, an assimilation approach to integrate discharge especially from the water surface elevation, from the altimeter and the rating curve to the model. So it's this assimilation approach is combined to our model MGB. We had it also when we assimilate discharge data in this platform. We also add uncertainty of our discharge. So this uncertainty based on the uncertainty on water surface elevation, but also on the rating curve. So if you need more information about it, please stay a little bit more for my colleague presentation in a few minutes, Slee, but you have also Vanessa's poster just in the next room. So now, what kind of improvement? So this is statistic. We have the KGE. It corresponds to the comparison between an assimilation with actual constellations, so basically JSON and Sentinel family, to the free run of our modeling. So we have for that 30 virtual stations were assimilated. And as you can see here, you have the mean discharge all over the main river here of the Maroni River. So more it's yellow, better it is. So we can see that it's pretty great, pretty everywhere. We have a KGE more than 0.93 all over the main river. For the low flow, it's pretty great also, but as you can see for the peak flow, we are not really great with a KGE less than 0.4 all over the region. So we want to now make exactly the same exercise, but to compare free run with an assimilated run with just SWAT Nadir 1 day constellation. So just here at this station at Papeston, because we have IGCP here, so we can reduce the uncertainty in this place. So this is a result. So as you can see, we have an improvement, a great improvement all over the main river, but not so much. It's pretty the same for the low flow, but for the peak flow, it's very significant enhancements in the to capture this peak flow. And if you want to make a zoom on the outlet of our basin, so you have in red the observation, in black is the assimilation with actual constellation. So as you can see, we missed all the peak here, corresponding to the flood in the region at this in this city. And now if we add just the assimilation in one point again, just here at Papeston, you can clearly see that we can reach with the blue line all the peak flow here. Here it's better, but it's not perfect. But you need to know that, as I said, we just assimilate here in this point, and we look at this point here at the outlet. But you have not just this river, you have also this one, which is corresponding, like you have a contribution of almost 50% for this one and 50% for this one. So if you have a big event here, you can miss, obviously, this peak. So what is very interesting here, so it's just ongoing work, so it's just few results that we've made with pretty the same team, the same type of exercise with the SMART phase A, and we had exactly the same result at the end, that we need to have more frequent data with a high temporal resolution. So the next step is now we have assimilated here at this point, but we have also in the SWOT Nadia track 3 other points, and it's very interesting because it's small river in this point, so we want to know how can we improve it. So we have already done the discharge time series in each of these 3 points, but we now need to put it on our assimilation and our model to compute it. And we want to also combine actual constellation with what Nadia one day to know if we can reach everything everywhere. So to conclude, and as a recommendation, so we have a lot of questions, a lot of context, and we need to answer to this actual problematic about the extreme events everywhere. And now we have developed end-to-end methodology. We could be ready for an operational system like Adrien showed you yesterday in French Guiana. And with just few results, we can see a better accuracy in discharge representation thanks to a high temporal resolution, and especially for the peak flow. So as a recommendation, as I said, it's very important to continue to have in situ data for everything, calibration, validation, and so on. And so it's very important to do that. We also need to continue to develop automatic retracking method to extract long-term water level time series from past mission like TOPEX. My colleague Malik explained it yesterday, to have a long time series, especially when you want to look at climate change. And at the end, as I said, we need to find a compromise between high temporal resolution, at least high temporal resolution, and if you want more, I want, with also high spatial resolution, and I'm pretty sure that we can do that. I think that's it for me. Thank you. Olago.
Thank you very much, and we have time for a few questions.
Thanks for a very nice talk. Your SWOT native results were really good. Can you share some information about the retracker you have used for that? And
For this question, maybe my colleague can may answer that. Taking them.
Yeah, it was my talk of yesterday. So it's the synchro tracker, and we try to use only one waveform, and so we analyze the transect, looking at what we expect to be the best observe the point. You just select one, and we use the synchro tracker.
okay,
on this
so
point.
you did not use the standard retracker that is in.
No, not the OCOG. No.
No, there is also a good new one, TFM.
Okay, so I didn't check for
Okay.
us what were
No,
certain.
thanks.
Yeah.
Sorry. Just to complement, we'll make sure that the data will be available to you.
Any other questions? There's time.
In your recommendation, the previous slide, you wrote high temporal resolution SWOT nadir. But
Yes.
is that like 21 days?
1 day.
Now? The orbit of SWOT is.
Yeah.
Yeah.
Until July.
Yeah.
That's why
Is that-
we use it. Yes, it's finished now.
Not operational.
Yeah, of course. That's why maybe Smash could be a good.
But isn't the SWOT
section for that.
swath going to be much higher temporal resolution than the nadir?
Temporal resolution over passing will be roughly 1 day, depending on the load. Higher latitude, sometimes up to. I don't need. That allows you to know how many positions you can expect what the decline of it. Plugin available on the web that will be aware about how many what.
You don't need the microphone because you don't want us to record it. It's recorded. We're going to amplify the sound. And we are looking forward for you to keep your promises.
Thank you. I had a quick question. In your open loop and assimilated data results that you showed, did you also look at data denial studies where you have observations? You're looking at results for 3 different locations where you're assimilating SWOT. So if you try to just assimilate SWOT at 2 locations and predict the 3rd location without assimilating SWOT, how good it is?
I'm not sure I understand your question. We assimilate just at 1 station for this result. For this one, here is just 1 station that has been assimilated with the SWOT. But I'm not sure that I maybe understand your question.
So are you, for example, the next slide that you had, not this one, the next one.
Sorry, the next one.
Yes. So aren't assimilating at 4 different points?
Yes.
So what if you just assimilate at 3 of those and take a look at the results at the 4th one?
Yes, we can do it. But actually, I'm not sure that we can do it because, I don't know if I have this. You can see it because the point is very huge, but it's in the small river just here. It's not in the same river. So I don't know if we can see something, but it could be a good idea just to check. Of course, yes. At least between this point and this point, we can just assimilate here and look at this point to see. Of course, yes, it could be a good idea. Thank you.
Thank you so much.
Thank you.
The next presentation will be given by Gabrielle. She's from KU Leuven And the title of the presentation is Assimilation of Sentinel-1 Data to Improve Estimates of Snow, Soil Moisture, Irrigation and Discharge in the Po River Basin.
Good afternoon, everyone. It's good to see everyone here. Before I start, let me acknowledge my co-authors, Louise Busgaert, Michiel Bechtold, Sarah Modanese, Zenko Hevaert, Izzy Sprengers, Hans Lievens, Augusto Gettinara, and Christian Massari. The research that I'm presenting is part of the ESA 4D-MET project, which Christian is actually leading. And so this is a consortium of KU Leuven, IRPI, and also collaboration with NASA Goddard Space Flight Center. So what do we want to do? We want to quantify water storage and water fluxes as good as possible in the Po River Basin. And we want to do that by using the latest advances in both land surface modeling and Sentinel-1 observations. So more specifically, our objective is to quantify the relative contribution of Sentinel-1 snow depth retrievals over the mountainous areas, so the borders of the Po River Basin, Sentinel-1 backscatter observations, which we will use in the valley to estimate soil moisture, and subsequently irrigation and vegetation. And then on the other hand, irrigation modeling, so advances in land surface modeling. And all that, we want to see the relative contribution of these three components to improve water cycle state variables, such as soil moisture, snow, and fluxes. And the focus will be today on stream flow. So land surface processes, they are well captured historically in land surface models. And just like Earth observation, land surface models have been moved towards higher resolutions, fine resolutions, multi-scale input. That's all feasible now. We also resolve more processes. We have more variables. We have better coupling between different processes in land surface models. For example, we are now able to model irrigation, to model groundwater, to model nitrogen cycles, all these things. And so that's advantages. That's a good background framework for us to do data assimilation. The model that we chose is the NOAA-MP model, which can be run with or without irrigation. It simulates vegetation dynamically. It's coupled into the NASA's land information system, which also allows coupling with HIMAP, which is a routing system to give us good estimates of discharge. We supply the NOAA-MP model with different parameters, including, for example, the land use map, which you see in the top left, where you see over the Alps and the Apennines, we have mainly forest and shrubland. Whereas in that yellow area, that's the Po Valley, really, where it is agricultural, mainly agricultural activities. The bottom plot shows you the soil texture, which is also important because soil parameters will tell us how much water is available for plants, for example. For this presentation, we forced the model with ERA 5 meteorology. I'm not saying that that's the most ideal case, but that's what we did for now. It's downscaled to the 1 kilometer resolution. So everything is run at a 1 kilometer resolution for 8 years during the period we have Sentinel-1 data. So that's the modeling part. For the observations, we're going to use the Sentinel-1 data. Sentinel-1, an active radar system, right? It sends and receives signals. We look at snow in the winter and in the mountains. We look at soil and vegetation in the summer and in the valley. That's the idea. For snow, we use a change detection method. Based on the cross-polarization of the Sentinel-1 data, we see really nice snow accumulation at a fine resolution over all mountainous areas. On the left-hand side, you see some examples, daily snapshots of snow depth retrievals. It's C-band. I know there's some controversy, but we have towers in the field that actually show the physical relationship between snow clusters and the radar signal. So the data is well validated across more than 700, 800 stations. The correlation there is 0.84 in time and space. So those retrievals are behaving really well, the snow depth retrievals. At the other hand, in the valley in the summer, we're going to use the backscatter data. backscatter, by the way, for us will be gamma. It's terrain corrected, so it's not the sigma, it's the gamma. And we're going to relate soil moisture and vegetation to the backscatter using the water cloud model, which we will calibrate at the point scale. Yeah, so it's that translation between soil moisture and vegetation and backscatter is an extra model that will be added to the land surface model. So we've had this model, we've had the observations. Now we do the data assimilation. So the data assimilation is a one-dimensional ensemble Kalman filter. It means, I have a pointer, yes. We run an ensemble of trajectories with the model, right? And whenever there is an observation available from Sentinel-1, either snow depth or a backscatter observation, we compare our model simulations against the satellite observation, and we make some weighted average to correct our model and then forward propagate in time. For the snow depth, we assume an error of 30 centimeter, and we only assimilate during the accumulation, because once snow starts melting, Sentinel-1 really detects wet snow, and then our retrievals are no good anymore. We assimilate snow depth. We also update SWE, of course, so the amount of water in the snowpack. For the backscatter data assimilation, we assume a 1 decibel error. That's after the calibration of the water cloud model. And that is going to be used to update only soil moisture, but all the other variables will respond to that. In the end, we'll have a self-consistent estimate of all the variables in the land surface. So snow, soil moisture, LAI, everything will be connected because there's no physical breaks anywhere. And we will have an uncertainty estimate on all these estimates. So some people call this a digital twin. I think it's just a good estimate of our water budget in total. How are we going to evaluate our results? In 3 ways. So state variables, including snow depth at those stations that we have available in the Alps. Soil moisture will evaluate against another satellite product, the SMAP downscaled 1 kilometer product. LAI evaluated against also a satellite product, the Copernicus product. In terms of fluxes, we evaluate against different evapotranspiration products. I'm not going to show that today because there's lots of biases between those. We need to sort that out. But I'll focus on the stream flow evaluation. That's an integrated measurement, so that's actually also a very interesting measurement. And I want you to just follow with me here how we do that. So for about 28 stations, we have the upstream basin, right, where water comes into that gauge. And for each gauge, we have discharge simulations, and we will withdraw irrigation if irrigation is simulated, right? We will assume that irrigation is withdrawn from the river to then be applied on land. So we will do the evaluation of discharge at a monthly scale because we don't know exactly what is withdrawn when. But again, we will withdraw irrigation from the simulated discharge to do our evaluation if irrigation was simulated. Final one is the data assimilation diagnostics. It's really good to say I do data assimilation, but you really need to make sure that your system is behaving well. So even though that's more technical, it's important to check. All right, so that brings me to the experiments. We have 8 experiments. We start. That's going to be easier. We start from the open loop, so a model-only simulation without any data assimilation, without irrigation simulation. And from there, we can either add irrigation to the simulation, we can do backscatter data assimilation, or we can do snow data assimilation. If we stay in this bottom plane, we have 4 experiments without irrigation. So 1 with snow data assimilation, 1 with backscatter data assimilation, and 1 with both snow and backscatter data assimilation. If we go to the blue plane, we add irrigation, and again, we can add snow data assimilation, backscatter data assimilation, or do all of it. And the hypothesis would, of course, be that if we do everything, things would be the best, right? Just for you, if you see S, it's snow data assimilation. If you see gamma, it's that backscatter data assimilation. And a star means with irrigation. So starting with irrigation, irrigation modeling depends strongly on the parameters that we give it. So salt parameters, crop parameters, the irrigation type. We evaluated that at some fields where we have in situ data, and you see here 3 years where gray are in situ data of irrigation, and in magenta you see our open loop simulations. Those simulations roughly correspond good enough, especially it's hard to model human activities. So I would say that's a successful simulation. The other lines are data simulation ones, which of course will have influenced also the irrigation. So that's good news. However, these two sites are located right here in the blue area. And if we look at our entire Po Valley, you see that our yearly irrigation is about 133 millimeters per year, and that's far too low. We know that we are irrigating about 300 to 500 millimeters, so something is wrong. And if now for each basin we would subtract that irrigation, because these are the basins, right, where we will evaluate the discharge, if we would subtract that irrigation, we're going to subtract too little, right? We know that from other modeling, and we know that from the observations that we have. So there's 3 fixes that are ongoing. For these results of today, I'll show you the results with the underestimated irrigation, but still the message will be the same. You'll see how it turns out. So 3 fixes are irrigated area needed to be expanded for paddy rice, which wasn't included. Our lower boundary condition was groundwater, but we found out that the surface layers are not that much influenced by groundwater, so we decoupled it and we have now free drainage. And I think that our meteorological forcings are not ideal. ERA 5 is largely overestimating precipitation in the valley, which causes that which results in too little irrigation. Yeah, so that's the main problem. So that's a limitation. Okay, the snow depth data assimilation. That's the other factor. So we have these types of maps from Sentinel-1. Over the Alps and the Apennines, we have snow depth retrievals. This is an example, 2020, February. This is an open loop simulation, model only, without data assimilation. You merge those two and you get a nice data assimilation results, which typically has much finer spatial granularity. You see much more details. And in this particular year, we actually fixed some bias as well. Yeah, so that's nice. At each point where we have in situ data, we have these types of time series. This is not a best performing site. This is just a mediocre site where you have the in situ data in black. The dots, the gray dots, are the Sentinel-1 retrievals. Yeah, and so the open loop is blue. We assimilate the gray dots in the blue simulation and we get the green simulation. So most of the time we really get closer to the in situ data and we get an uncertainty estimate, which is, I think, in general, nice to have. This is the skill. In general, for all these sites, we improve the skill in terms of relative mean absolute error. Relative means it's divided by the absolute value of the snow, because some sites have a lot of snow, others have far less snow, right? So overall, it's blue, and the snow depth data assimilation really improves the snow depth estimates. We've had irrigation, we've had snow data assimilation. Next one is backscatter data assimilation. To do the backscatter data assimilation, again, we need the water cloud model. And there's 4 parameters in that model. So these are the equations. Don't worry too much about it. It's a soil component and a vegetation component. The vegetation components have the parameters A and B. You see these values are low, so we're going to suppress a little bit of vegetation in general. The C and mainly D parameter are sensitive to soil moisture. So the higher these D parameters, the more sensitive the backscatter is to soil moisture. Out of this calibration, which is an advanced Monte Carlo calibration technique, we also get an estimate of the backscatter error, which hovers around 1 decibel, right? So that is also the reason why in the data simulation, we then use 1 decibel as an error estimate. Okay, the result of the backscatter data simulation. We evaluate soil moisture versus the SMAP 1 kilometer data. So top left is just the open loop without any data simulation. And you see that our model performs well in terms of unbiased RMSD. We're typically below the 0.04 target uncertainty. That's like a rule of thumb we want to meet. We have a little bit higher over the area because we have that paddy rice spot, which really we should have filtered out, right? Now, what's the effect of the data assimilation? That's the right-hand side panel across all the years. You see that in general, we decrease the unbiased RMSD. So that's thumbs up. That's a good result, right? So we assimilate Sentinel-1 and we get better results relative to SMAP. Now, I have to say that this nice result, this improvement in unbiased RMSD, is actually a result of improving our seasonal cycle. If we look per season itself, we see very mixed results. So in some seasons, we have lots of improvement, but in other seasons, we actually have a degradation. So it's important to also look within each season. And that's further ongoing. That's the effect on soil moisture. If we do backscatter data assimilation, that also affects LAI, evapotranspiration, and other variables. Same with irrigation. What I'm showing here is the effect of these two, irrigation and backscatter data assimilation on LAI. Very similar plots for evapotranspiration. So top left is just our bias in a model without any irrigation. And you see that we underestimate LAI. Sure, right? I mean, there's not enough water. The model will not simulate enough LAI. If we add irrigation, then go to the bottom plot, we fix a lot of that. So we improve or we decrease our bias by adding the irrigation. That's the left-hand side. Right-hand side, you see the impact of the data assimilation, the backscatter data assimilation. Top is our anomaly correlation of just our open loop, our model without data assimilation, performing relatively well. If we do backscatter data assimilation, unfortunately, we do not improve our LAI. That's a known problem. Also, in terms of evapotranspiration, it's not helping us much, right? So that's the limitation. Now, the main result for today, the take-home message, is the evaluation in terms of stream flow. So here we have all the 8 experiments. In red, again, the simulation without irrigation. In blue are all the runs with irrigation, right? The first bar is the model only without data assimilation. You see right away that even though we underestimated irrigation, right? That's the limitation of this talk. You see that we are improving the correlation, but also all the other skill metrics like Kling, Gupta, Nash, Sutcliffe, all these other metrics are improved, right? If we do snow data assimilation across the year, it's not really helping our year-round metrics. Backscatter data assimilation is improving a bit, but in total, if we do an irrigation and backscatter and snow data assimilation, indeed, we get the highest performance, right? I said here, snow data assimilation didn't help us so much across the year. That's because in the summer, we didn't improve it. However, in the spring, and that's the top left here, you see the effect of snow data assimilation compared to an open loop. Basically, for all our stations in this Po River basin, we improve our discharge, which is nice, right? The snow melts, and in the spring, our discharge is largely improved. So that's a really nice result. Bottom figure, it's the impact of the irrigation. So a model with irrigation minus a model without irrigation mainly improves our discharge in the summer. So that's another good result. For the data assimilation diagnostics, I'll go quickly over that. The top is the bias in snow, and in backscatter, you see overall we have an unbiased system. Bottom is just to see if our errors are well estimated. I can tell you that for snow, we actually overestimated our errors. In terms of backscatter, we did a good job. Right? Quickly speeding up, if we look at the different seasons though, you see that in backscatter data assimilation, we add and we subtract soil moisture per season. So overall, over all the seasons, over the entire year, it's an unbiased system, but per season, we actually have a bias. So to conclude, irrigation modeling definitely improves soil moisture, LAI, ET, and that's mainly a bias reduction. Yeah? It definitely improves summer discharge. And depending on the model settings, we will further improve that irrigation. Snow data assimilation, it's undeniably helping our snow depth estimation, and it definitely improves our spring discharge. We need to look into what it does in the summer, but spring discharge is definitely improved. Backscatter data assimilation improves soil moisture, the effect on evapotranspiration and discharge varies depending on the coupling in the season. Yeah. Also, I want to note that there are seasonal variations in both our skill metrics and in the data assimilation diagnostics. And then there's the recommended slide, right? The outlook and the recommendations. I think we can get big improvements still in our models by making sure that we include human activities, such as irrigation. I think here our discharge is definitely improved with irrigation estimation, even though our irrigation wasn't even that great. I think we really can explore our Sentinel-1 data more and trust the data, right? There is so much in it. The backscatter isn't entirely used, I think, to its fullest capacity. Our model complexity is increasing. That is happening. And at the same time, I think we need to leverage our observations to guide our modeling, right? So it's not only that we want to improve our observations using models, but we want to use observations to fix our models as well. And then a final one, I think meteorological forcings remain really critical. We are focusing on salt marshes, snow depth, but the forcings remain really critical. Thank you very much for your attention.
Thank you, Gabriel. We have time for one quick question.
Thanks for very nice and didactical presentation. I have a question. So maybe you have explained and I missed that. How do you quantify the uncertainty for the observations?
Yeah, so for the backscatter, that uncertainty falls out of the calibration. So we calibrate the water cloud model. And from that, we know afterwards what the remaining uncertainty is between the observations and the simulations. That's for the backscatter. For the snow depth retrievals, we evaluate our snow depth retrievals against in situ sites. And that error, a little bit amplified because we added some representativeness error, is used as our observation uncertainty.
And is it really normally distributed? Because when you feed it in the Kalman filter, you have a huge assumption of Gaussianity.
That's true. That's a good comment. I think I think it's close to normally distributed, but maybe not entirely. Like the model for sure, it's not the resulting uncertainty is not Gaussian. It's an ensemble and it's twisted. That's for sure.
Okay, thanks.
Thank you, Gabriel.
Thank you.
Our next presentation is titled Improved Modeling of Congo Hydrology by Representing Lake Storage Dynamics and Data Simulation. And the presentation will be given by Sly from Lagos.
Hello, everyone. Thank you for being here, attending this session. And also thanks for all my colleagues that collaborated with this study. So in this presentation, I want to show you some results of a paper we recently published in which we improved the modeling of hydrological and hydrodynamic simulations in the Congo Basin by implementing lake storage dynamics representation and also data simulation techniques. Okay, so as previous presentation already shown, as Mohamed, for example, just to contextualize the importance of the Congo Basin is the second largest basin in the world after the Amazon. So it covers an area of around 4 million square kilometers. And around 50% of this basin is covered by tropical forests. And because of its host a large biodiversity, and because of its size and also strong hydrological signatures, it plays a crucial role in, to control the global scale climate. And also this basin, similar to the Amazon, this population highly dependent of the water resource availability and ecosystem services that it provides. So the Congo Basin has a really big issue in which there is a limited understanding of this large-scale variability of hydrological components and also their links with the climate processes. So just to make a quick research in Scopus, if you look at keywords like Amazon, Congo, or basin, or climatology and hydrology, we can see that the Congo basin has around an average 4 times less studied than the Amazon. So, so a scientific question remains, and how is the spatiotemporal dynamics of water in the Congo, and how we can measure it. So for that, and also now first we have hydroclimate records, we have in situ records in the Congo basin, but that has become less available in recent years. Just an example, nowadays we have around 3 stations that are maintained and available. So it's 3 stations for a basin of 4 million of square kilometers is really crazy. But however, we have increasing long-term Earth observations data sets from space that could complement and also extend these in situ records. And second, we have also hydrological and hydrodynamic models. So different types of models, statistical and also process-based models have been developed in the last years, but they have some issues, as for example, they didn't model the lakes representation, which are really important in the southeastern part of the Congo basin. And also recent techniques as data simulation have been developed in the last years that have been applied in large-scale hydrological models. So in this study, we proposed the developing of hydrological reanalysis, which we took this concept from climatic and oceanographic fields, in which we used model simulations and also observations in an optimal combination by using data simulation techniques to have a state of the art of these of different variables, hydrological ones. So this is the paper we recently published. So the main objectives were first to improve these estimates of river discharge in the last 40 years, but with the objective of study extreme events, extreme hydrological events such as floods and droughts. And second, we evaluated the potential hydrological hydroclimate triggers that are teleconnected with specific extreme events. But in this presentation, I want to focus it in this first objective. So for that, we used a hydrologic and hydrodynamic model, the MGB, as my previous colleagues presented. So in this model is a large-scale distributed model in which the catchment is discretized in unit catchments and further in hydrological response units, in which we computed the vertical water balance, and then for each component, superficial, subsuperficial, and groundwater component, reservoir, is routed in through each unit catchment until the river, and then it's propagated by using a hydrodynamic inertial model. So, which is really important in the case if we want to represent processes in, for example, in areas with floodplains or low slopes, or to represent backwater effects, which are really important, for example, in areas like Amazon or Congo basin. And then in this specific study, we implemented the lake storage representation. So we know that in the Congo basin, many of these reservoirs are natural. It means are lakes which are not not controlled. So we implemented a simple model, a simple lumped reservoir routing by using the equation the overflow spillway, on which we have 2 parameters which could be calibrated. And then we implemented the data simulation technique, which is the local ensemble Kalman filter, as my previous colleague also presented. So I won't enter into detail of that. So we implemented this model in the Congo basin, and for that we use it as much as information as possible. So we took around 13 in situ station of discharge and water level, and also this historical monthly series of discharge, which unfortunately were located close to the lakes, as you can see in the southeastern part of the Congo basin, which we use it to calibrate the parameters of the lakes. And also we use the legacy of all available virtual stations in the Congo Basin from JSON, Invisat, and also Sentinel-3. So all these stations were used for calibration, validation, and also for data simulation. So as a experiment setup, first we want to calibrate hydrological and hydrodynamic parameters. So we divided our 40 years of simulations in 2 periods for calibration and validation. So once we have our parameters calibrated of the hydrological ones and hydrodynamic ones, we calibrated also the lake parameters by using, as I told you before, historical monthly discharge areas. And also for validation, we used virtualization from lakes that are already available in the HydroWeb site. And finally, once we have our hydrological, hydrodynamic, and lakes parameters already calibrated, we used data simulations to further improve these simulations. So we used a cross validation technique. So we took some stations with the longest period for a simulation purpose, and then we used the remaining ones for validation, and then we did the opposite for the complete this cross validation. So just to present these results that could be really boring, but so we achieved values of in average of Nash-Hood cliff of 0.84, a Nash of Klingupta, sorry, of 0.8, and Nash of 0.7. But more than this efficiency, we want to go to the dynamics of this hydrograph in the Brazzaville station, which is the station with the largest contribution area. So we can see that we more or less we could represent the bimodal phase, bimodal behavior of this region, which is not so easy to represent. This incertitude could be attributed to the precipitation inputs also, and also to hydraulic parameters, which we try to calibrate it, but I think there is more effort to do. And then for the validation period, well, so we achieved relative satisfactory results, which Klingupta result of 0.7 and Nash of 0.5. And this is just an example of the dynamics we represented in this station in Hueso. So we could see that we satisfactorily represented at least the interannual variability in this region. So for the lakes calibration, in this map, you can see the impact of the implementation of the lakes representation. So it's coherent that in rich rivers closer to the lakes, the impact is larger. So this index is just a ratio between the discharge, between the model without lakes representations and the discharge with lakes representations. So larger values means that the model without lake representations overestimated. So this is current because if you have a lake, an estuarine, you can attenuate these discharge processes. So after the calibration, you can see that in this figure, in blue, the observations, in red light, the model without lakes representation, and in red dark, after the calibrations, you can see that we could have an average reduction of errors of around 80%, which is larger for this implementation. So for validation, we also can see that when we validated the water levels, we improved the lag of the hydrograph and also the volume. So we passed from negative values of Nash to positive of 0.3 in average. Okay, so once we have this model that is already calibrated by using in situ discharge station and also virtual stations, so we go to further improve this simulation by using data simulation. So as a result, you can see in this map the first validation experiment or data simulation experiments where we have, for example, the simulation stations were in triangles were the stations with longest information. So we can see that we improved around in average 13% of reduction of errors. And as you can see in this hydrograph, at Brazzaville stations, so this station was used for data simulations. So you can see that is a good agreement between observations in blue and the black, which is the data simulations. So in red is the open loop. It means the model without simulations. So it's coherent and it's obvious because this station was used for data simulation purpose. But when we look at the station, what was used for validation, we can see also that we have some improvements and trying to recover the bimodal behavior on this region. So we had an average reduction of errors of 20%. So the same for the second experiment for data simulation. In this case, we have also an average improvement or reduction of errors of 13%. So as you can see, we recovered also the bimodal phase behavior of this region. And also, if you see at the Brazzaville station, that's in this case was a station used for validation station, you can see that better improvements were mainly in the second part after the years 2000, and this could be explained because in this period we used virtual station also for this data simulation experiment. So now we have a model that is already calibrated, and also we proved that our data simulation experiment really works. So why we do that? Why we do these experiments? So the next step is to use as much information as possible. So to create this hydrological reanalysis. And why we did that? So because our main objective was to study the past, in this case, extreme events. So in this temporal series, you can see the seasonalized discharge at Brazzaville station, the station with the largest area contribution. And we established a threshold to see if this, to compute if this specific year have an extreme flood or an extreme drought. So you can see that, for example, these both observations and our final product really agrees with a correlation coefficient of 0.95. And with this final product, we could be able also to spatialize these specific events, as for example, the extreme flood in 1997, 1998, which really impacts not only the Congo, but also the Amazon basin. And we could be able to spatialize this impact. And also, one important contribution could be to also relate this specific event with large-scale processes, such as, for example, El Niño SST, which is the sea surface temperature in this region, a specific region of the Pacific Ocean. So, as a conclusion, we improved accuracy of daily discharge. During the last 40 years, we could be able to detect and map specific past hydrological extreme events, such as floods and droughts. We could be able to represent seasonal and also interannual variability of river discharge in many places in the Congo Basin. So as a final product, we have these long-term records of discharge. So this dataset is available in this repository if you want to use it as a benchmark, for example. So as a recommendation, until now, we only use it, for example, water surface elevation and also in situ to these simulation experiments. But we can also use remote sensing information which could be good in the sense that we could constrain our model to be more physically representative. And also it could be a short-term solution before we could have like a constellation of a small SWOT or smash constellation, because if we have multi-observations, we could fill the gap of the temporal sampling of only using a single data set. So it's all for me. Thank you.
Thank you. Questions for the speaker?
Thank you for the presentation. I'm wondering, in the Congo Basin, isn't there a big peatland as well? And what is the relative impact of that peatland compared to the lakes? Is that peatland well modeled with the current model?
Yeah. Actually, these peatland are simulated because it's an hydrodynamic model, and we didn't check the improvements in these specific regions. So we, in this specific study, we only simulated 7 lakes, the biggest lakes, not all the lakes. Probably, I don't know if this region you mentioned it are simulating our models because of we only focused in the bigger impact. Probably because also our study was focused in more large scale. So probably in another, in further studies focusing in local scale, we could be more precise to try to simulate these processes.
Thank you.
You're welcome.
Any other questions? Thank you so much. We move on to the last presentation of the session. Presentation is titled Towards High Resolution Volume Variations from Space Remote Sensing, and the presentation will be given by Christopher.
While it's set up, I have an announcement to make. At 1:30 at the end of the session, you're all required to go to the staircase where we will do a group picture just at the beginning of the lunch break.
Thank you. Thank you. So now it is my turn. Thank you for being with me in the North Pole again for the last presentation of the day, of the morning, sorry. I promise you I won't be that long. I'm hungry also, but I'm still here to talk about high resolution volume variations and some different approaches we have with my team at CLS towards the estimation of volume changes and in some cases total volume assessments. So the idea here, if it, no, well, it's going to be handy. Just for the outline, we will begin with the context of water volume estimation, of course, following with the first solution, which is already applied in some cases of mixed hybridizing altimetry imagery. And when we have no information about that, a workaround when no altimetry data is available, and in the end, talking a bit about some total volume estimation from AI, and of course, following that, a summary and some perspectives to go forward in that endeavor. So if we take the context of water volume estimation, we have few continuous and long-term measurements of water height. We already know that. Surface area and volume variation at a global scale, despite an increase in number of efforts to that end. And it's needed for two main purposes. The first one being climate change monitoring. We need long-term assessments of volume variations to improve the models and better understand the climate change. And also for water stock management for the users at a regional scale. So there are already existing approaches with altimetry and imagery. I'm thinking a lot about HydroWeb, but also Dahiti, of course. And we want to explore also new approaches to increase the number of water bodies that can be monitored presently, but also in the past through the use of DEMs. But also we wanted to explore the use of AI and what they can provide to us if it's well performed to retrieve total volume estimation. So for that, we are having R&D activities with our partners of CNES and ESA. Because sadly, with JSON Sentinel-6, Sentinel-3A, and 3B, only 10% of the worldwide lakes in the Hydro-Lakes database are covered for the moment. The biggest are covered, but the smaller one aren't yet. Because yes, SWOT, I think you heard about it. Is an absolute game changer and is going to provide a lot of information for 97% of the world, at least once per 21 days. So it's going to provide a huge amount of data. But to begin with, the first approach is a common one, commonly known, is to say mixing information about water surface from imagery and water elevation from altimetry to provide water storage change from a lowest reference. So we have here in the downside, the altimetry corresponding surfaces, and if you mix both of them, you retrieve the hypsometric curve estimation. You make the estimation, if you're integration, what do you get? A lake storage change time series. So that's a common approach. It's a very known one, very well documented. And with Hydro, we have 500 water height time series of lakes, which are getting increasingly used to provide information about water lakes. If we go a bit farther with those data, if we use that hypsometry curve with very dense surface time series, what we get here in this lake in southwestern France, we have close to 1 data per week. And through the surface, you can estimate the height, derive the lake storage change, and in case you have the information about the total volume needed, the total volume, you can retrieve the fill rate of this lake. In that particular case, we had a huge drought by the end of 2022, but it's not exactly what we see here. It's the both impact of drought, but also they depleted the lake for maintenance. So it's not exactly climate change impact here. So we have almost a weekly pace, at a weekly pace, a storage change information here, when altimetry, in that particular case, provides information every 27 days. And we still have ongoing improvements to go deeper into the rising number of surface information using soil images and also using partly covered areas, filling the holes when we have clouds, for instance, or sadly an image that doesn't cover the whole lake. So that's fine. It's a very good approach. It works. But what to do when we have no altimetry data? So the idea here is to use recent DEMs, and I will explain later on why recent with water surface time series, as it can do the jobs. So for instance, here we are in northwestern Ethiopia. We have the huge new Renaissance lake, which has been filling up since 2020. And so we have the bathymetry and the DEM corresponding to both with SRTM, with merit, but of course here the COPDEM Glow 30 DEM. So the idea here is that if we take the contours of every Sentinel-1, Sentinel-2 images, we have a different date, and take into account that one contour corresponds to one height, we can retrieve the information about height. And well, even though it seems obvious, it's important because first, if we only have information about in one part of the lake, you can retrieve the information for the whole lake because we can retrieve the hypsometry curve here from the whole empty DEM. But also, there is a virtual station, in fact, which is here. But sadly, because the water level increased so much, the observed area doesn't correspond to the new water level. So the virtual station doesn't work anymore in that hand. So we have no information about the height in that place, but we have about the surface. So mapping the water surface body from a DM to get the storage change estimation is also something we want to produce at a large scale. To expand also the time series backwards, as I'm going to show to you just in the slide after all, and to estimate water height also when we have not only altimetry information, but to densify the information and hybridize all the data sets that are currently produced from all satellite missions. So if we take this example in Turkey of the Burdur Lake, I have no idea of the pronunciation, I'm sorry. We have here a lake about 25 kilometers long here, and we have some orbits here from Cryosat in yellow and Sentinel-3B in green. So here we have information about altimetry. The issue is that cryosat-2 began working in 2010, so we have only information after 2010 and nothing before that. But we have the imagery of Landsat 4, 5, 8, Sentinel-2, Sentinel, yes. And we have also information about the DEM and the time production of the DEM, which is 2011 to 2015. And this information is important because in that particular case, we see that something happened here. We don't know what exactly, but it seems it has been depleting. So if we have information on the DEM at that particular date, that means that before that, we can retrieve information because yes, we have a lowering level here. Yes, it's hidden. It's for the magic of the presentation. Some information about the surface here, a first hypsometry curve, but if we make a selection of Landsat surfaces and if we take the contours, we can go back in time with high precision, improve the extent of the hypsometry curve, and so derive the lake storage change from 1984 until now. So what did happen here? We went back to the past. Went back to the past because now we can, with high precision, go from 1984 onwards without any information of altimetry before 2010. Another example here, and to show the accuracy of the approach, we have here information with Sentinel-3A about height on this particular lake of Alberta, Canada. And we have applied the same things to say surfaces from Landsat from 1984 until 2016, which was the lowest point. And with the contours, we retrieved a height estimation here in blue and compared with the in-situ measurements from the Alberta Lake Monitoring Society, thanks to them. We can also enhance a lot the information about water volume changes for 40 years. So that's interesting. We have a lot of information. We have volume variation from a lowest point. But what can we do if we want to get to total volume estimation? So just before that, it's just a first attempt because it's an interesting approach, but we don't know exactly to how many lakes we can do that. So in the framework of the ESA Lake CCI project, we have 2024 lakes, which are being considered, as presented Jean-François Créteau on Tuesday. 1,600 of them correspond to natural lakes if we follow the hydro lakes classification. And if we take into account the global surface water change dataset of PECL for GRC for natural lakes, a quarter of those 2,000 lakes show neat loss between 50 and 100% surface change correspond to 50 lakes, and between 5 and 50% surface loss corresponds to 150 lakes. So we have, it's just a first attempt, it's a work in progress, so don't take it as something very clear, but it's something we are working on to assess to how many lakes we can do that. And that approach, I didn't show it here, but for just a small lake here, the Strobel Lake in Patagonia, in Argentina, which has only 0.1% surface change from 1984 till now, we have a very good precision also on the volume change estimated. But that only works from a lowest level. So what to do when we want the total volume assessment? And that's where we wanted to develop and explore the potential of AI to estimate the bathymetry of reservoirs and map water surfaces to get the volume. Because the idea is that from a field DEM, we want to dig it and reconstruct a bathymetry that might be realistic. So I won't go into details a lot for the moment because it's still a work in progress with CNES for the moment. A project about to end, but if we take an example here in the Guadalquivir basin in Andalusia, southern Spain, we chose to test the algorithm on the embalse de Isnájar, which is something like 5 kilometers long. And here we have the field DEM, the water mass corresponding in red, and in blue, the area taken into account to create the hypsometry curve, and we can see that we have not the information here. in red. But using the algorithm, we created the bathymetry, which is very realistic, but it's displayed here and it shows continuity with the area which is above this level. And if we compare with in situ information we got here, we can see that we have less than 10% error on the total volume and not only the volume change from a low reference. And then in another example, less than 10% error, and taking an example close to Toulouse, in France, we have the Lac de Gimone, which is 3 kilometers long. We have a field DM at the beginning, and using the algorithm, we recreated the bathymetry, and so we got this hypsometry curve. And so integrating from the water area displayed here, we got also the total volume estimation with precision which is lower than 5%. It's to say we have a very good precision on the total volume estimation for reservoirs. So just to sum up a bit and show some perspectives on the current work we were doing, the retrieval of lake storage change from altimetry and hypsometry curve is robust. It's well known, it's well documented. And for future integration of new water heights, we are waiting for the data from SWOT and ISA2 processing. So increase the number of lakes, reservoirs, and information we can provide. When you have new altimetry, DM and contours might save the day from 1984 until now. We also have an improvement of the frequency of volume change data by increasing the number of surfaces that can be used. Just a small example here. It's not something out of this world, it's something known, but with Landsat 7, if you have holes, you can fill it with an a priori information, and then you can recreate the surface. So if the surface is only partially covered, or if you have clouds, well, you can produce the information. A great perspective that should be the use of really precise DEM with the future CNES mission CO3D, which might be of sheer interest. And also, what about global COP DM, well, DTM at 10 meters, because we only have that for Europe, and it's an elevation model, not a terrain model. And if you take into account the storage change with the AI approach, well, we are expecting to begin large-scale production by March, April 2024 to provide as much information as possible in that frame. So thank you for your attention. If you have questions, well, I'm here for that. And we have something like 5 minutes, so please.
Thank you so much. Questions for the speaker?
Thanks for your talk. I have two questions. The first question goes, did you check your results with the data that Jean-Francois presented?
Of course.
The work from Yao et al.?
Yes.
How good or how bad is your result against that one?
Well, we have less than 1% difference, so.
Okay.
No, it's very good.
Okay. And so AI is by itself a black box. You managed to make it a black box. You did not explain how it is actually estimated. Can you elaborate more?
Well, the paper is actually under production, so I won't explain everything, but we created a huge database of virtual lakes.
Okay, but what goes in? What I mean, is it
The
leaving
DEM,
out of features, or
you just have to provide the DEM, the water masks corresponding to the pixels corresponding to water, and that's it. It produces a bathymetry, and then you can retrieve the hypsometry curve for that.
So it's kind of magic, because
as Freddie Mercury said, yes, great philosopher. It doesn't always work, but it's presenting impressive results.
Which is the limiting area that you think that you can achieve with that?
Well, we're currently working on a multi-size approach, is to say using Merit or Copernicus DEM, we can take into account smaller reservoirs, large reservoirs. And we are working to see if the degradation of some DEMs for very large reservoirs would show good results also.
If you want to put a number, 1 kilometer square is what? Small, medium?
Well, the Lac de Gimone was 2.5 square kilometers, so 1 kilometer might be doable. We're still investigating it, but for instance, we can, well, I didn't show it because those results are far too recent, but for the whole of Guadalquivir basin, taking into account the 21st biggest reservoirs, we assessed a filling rate of 20% when the reality is 22%. So it's kind of impressive. But sometimes it doesn't work. We're still assessing why it doesn't work, to what extent we can be sure about the data. And all those methodologies want to be mixed together to provide large amounts of information, precision, and also work on the quality flag, because that's something that is missing. And we need to know the error that we can make using those.
Thank you.
Those methodologies.
Sorry, I just missed the first part of your presentation because I was there with the Wagner's presentation, just blaming AI. But just a quick thing, you mentioned that there are some cases that you found it not successful. Have you checked that it's just because of the data for training, the problem with the data it is the case, or something gets missing or out of the distribution that you wanted, or it's just problem with the model or parameters?
We're still working on it. It's to see, maybe it's something that hasn't been well trained in those particular cases, but we have to understand why. Is it, in fact, the DEM? Is it the width of the lake, of the reservoir, I should say? We're still digging it to be able to provide very precise information in those cases.
And was this important for you that the features that you put as an input have some correlations or relationship with each other, or you put anything as the input and the model is going to take care of it?
It works that way.
Okay.
And with Copernicus DM, we have a water mask, so it's very easy to use. Copernicus DM, you just put the water mask, please dig that in that area, and it does it. It's kind of cool.
Thank you so much. Let's thank the speaker. Thank you for all the presentations. I do want to have some time for some discussions of some, so we can provide feedback to Jerome and the committee. So one of the first questions I would like us to discuss or think about is, since the session is titled EU Observations for Land Surface Hydrology, what are the critical land surface hydrology variables you think are missing or lacking, either in spatial scale or in temporal scale, or the variable is missing that is a critical part of the error budget? And how does that impact climate studies also? So if somebody has any thoughts on that, what are the critical missing variables?
Like irrigation, for instance? Is it critical, according to you, to know, to have more observations or to get more information on the irrigation amounts, supplies, etc.? Or not really?
Somebody has any comment?
Yeah, any water management, I would say, is important, human water management. The other one, I think that we don't know, well, with as much accuracy as evapotranspiration. I don't think there's maybe evapotranspiration experts here, like, but that's one of the big fluxes that we don't know accurately of. Snow in mountainous areas is another important one, according to me.
Thank you. Just to add to that, I think discharge from reservoirs is another thing that we lack, especially if we are trying to do stream flow monitoring downstream. That's something that we don't have a good handle. That's basically managed by the water authorities, and that data is Depends on whether they are willing to provide you or not. Any thoughts on spatial or temporal?
If we go for the impact of humans, I think then you really need to go to high resolution, both in space and time, because you need both in that case. For climate applications, I would say we're pretty good right now. That's my take.
So try to hit our multiple. Go ahead, please.
No, maybe just to go back on irrigation. Yeah, I think it's of course an important issue because it's taking lots of water. And even I was thinking at the beginning when we talk about SWOT mission, I was thinking because you have some large, I think about 80%. Okay, you have irrigation from groundwater, but you have irrigation from irrigation canals. And I have in mind that about 80% of water for irrigation is coming from big irrigation canals. Maybe I am wrong, but I have in mind it's a quite important percentage. And I was thinking with the quality of data we have seen with SWOT, where you can see water bodies like 10 or 20 meters wide. You have huge irrigation canals. If you look at in Pakistan, you have these Fordwa canals, and they have like 100, 200, 300 meters wide. So I think also SWOT maybe would be interesting to see in this irrigation. Sometimes you have water measurements, but it's not available. And for me, looking at irrigation canals with SWOT is probably also something interesting, as that can give some information. Like on the Po River, you have this big Emiliano Romagnolo irrigation canal, and so when you had your presentation, I was thinking it would be good also to see on this canal how much water they're taking, and sometimes maybe it could clarify your estimation of irrigation on this area. So for me, definitely irrigation and irrigation canals can be a interesting objects we could study.
And is it a problem if the irrigation canals are not in the SWOT database? Can we still extract some data?
Yeah, good. Yeah.
Yeah.
Yeah, it's not in the SWOT database, or maybe there are some canals in SWOT database, but yeah, I didn't check. But Roger has some.
Yes, I mean, if it's not in the database, the good thing to do is to add it. So if you find things that are missing, you can propose to add them to SWOT or to the lake database, depending on what it is. So, and then of course, I mean, we have seen cases where we see water bodies down to 10, 20 meters wide. It's not sure that we can extract precise height values when it is really, really small. But it's worth checking. And also, I mean, if you want to test it yourself, if it's not in the lake database or in the river database, I think I wrote it on my slide, but I don't think I had time to say it. Both river and lake processing is open source. So you can actually rerun it yourself and even do modifications to the way river and lake processing is done. So so on one hand, you can test it yourself, and on the other hand, you can also propose to add water bodies to the prior databases.
I mean, I think that if they are not in the SWOT, they will not be available. So we have to add it, the canal, right? Yeah. 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 Yeah.
So the other thing that I think is probably missing is the wells data, because a lot of the irrigation and is by just pumping of the groundwater, and that we have no clue about how much is being pumped.
Thank you. Maybe something which is missing here is that we can integrate also other kind of data like the land surface temperature information, the thermal infrared data, which for also knowing and having better estimate of irrigation could help as LST is part of the evapotranspiration. So it's something that probably here is not very present, but it's a big community working also on this. And if we can complement the soil moisture with the land surface temperature, probably we can also better have information on also not only evapotranspiration, but also irrigation.
Any other comments? I'm going to throw out another question. So, as you probably know, land surface hydrology needs a lot of ancillary data. What do you think are the missing ancillary data sources that have the highest uncertainty that are leading to errors in the land surface hydrology?
I take both the dynamic land use, so land use is changing in time, that's missing, or it's very limited. And I think our soil texture is another one that's not that great.
I would second the soil texture, especially not the surface. The deeper, we have no clue. It's just an absolute black box. Top layer, we may have some clue, but the bottom layer is like, we're clueless. Any other
Could
sources
these
of error?
and could these aspects be like a land texture, for instance, be improved by data assimilation? You think? Into land surface model, I mean, assimilating different kind of observations, like surface soil moisture, for instance. Could we improve maps of soil texture with that, or any other component? We could think of assimilating grace data to recover groundwater. Is it reliable? Do we still have a lot of uncertainties with such approaches, according to you?
It's a whole different scale because hydraulic conductivity is really small scale. Grace is kilometers wide. I don't know if you can get anything out of that. You can tune things, but tuning is tuning. I think it becomes other thing that I think Gabriel touched on is changing land cover. It becomes more important as you look at climate studies and impact of climate change on land surface hydrology and land use. So that's also a critical variable.
Yeah, I will just have a short comment. It might sound provocative, but that's really not my point. I've seen some very nice presentation about data simulation with distributed hydrological model. So very sophisticated with a big machinery, a lot of modeling inside. And at the end, the end result was, at least what was shown is discharge as the outlet, basically. And with NSE, which was very good, of course. But in other presentation, you could see very simple bucket model, conceptual model, 1 or 2 equations, achieving exactly the same thing for discharge prediction, discharge modeling. So my point is that I've been a bit frustrated because with all the result of all the distributed, sophisticated models that have been presented with data assimilation of many observation, I would have expected more than seeing only the discharge at the end, but also, yeah, exactly to come back to this, other parameter, physical parameters that's we don't have access, direct access to. But that you can probably at least improve with the data assimilation. Because otherwise for discharge prediction, I mean, if you look in the literature nowadays, you might have also simple you know, neural network, LSTM, all the things that are black box, okay. Also, it's not totally true now, but that achieve way, I mean, state-of-the-art prediction, even if we don't know exactly why, but that's the point. So all the hydrological model, distributed model with a lot of physics inside, yeah, data assimilation will be great, but what I would have expected to see is also yeah, result on more physical process quantification of this process.
Yeah, I completely agree. I think when you're doing data assimilation, we want to make sure the different state variables, which are the water cycle state variables, are looked at, not just the stream flow, but if you're doing soil moisture, sorry, soil moisture correct, is if you're doing, you have ET processes there in the modeling, then is that correct? Two wrongs don't make the answer right. So that just becomes an absolute black box then.
Well, I don't completely agree with your remark, because some of the results were showing discharge not only on the outlet but of the entire river network, and such applications could be seen as a kind of physical interpolation of different observations. When you have an observation there and another at this time and another one downstream at another time, you won't do a simple linear interpolation, you know. And using a kind of hydrodynamic model with data assimilation helps you interpolate with the physical constraints. On the other hand, we can also, so maybe not really in the presentation there, but data assimilation in such model are also used to point some specific missing processes. I am thinking, for instance, of detecting irrigation fields by assimilating leaf area index into a land surface model. And for instance, at Meteo France, we did such a study, which has been published a few years ago. And it was very interesting to see that without any consideration of irrigation within the model, just by assimilating leaf area index at quite high resolution, I mean, something like kilometric or 5 kilometers, we clearly see the extent of irrigation fields that we could get from any other maps, for instance, over the Ebro Basin. So the data assimilation can also be used for such purposes. And to retrieve some physical variables, such as or constants, such as for instance, the roughness. Well, for the roughness, to me, it's a bit model dependent, because roughness is not only really the roughness within the river, but it also takes into account some deficiencies of the model, and so it depends on the equations, and so I think hardly it is hard to transpose such kind of results to another model, which could be really nice. But it's also the question I had just before about the soil texture, which is maybe something more common between models. We use basically the same databases, and maybe data assimilation could help improving such a database, which could be used in other models. But really, I don't know if it gets sense or not.
Any other comments? Think with.
Yes, I agree with the previous comments, because we usually look at the discharge because there is a degradation of all the processes, and when we do data simulation, and we usually update all the other variables, state variables, but not necessarily the parameters of the model. So so when we look only to the discharge, we could we could mask a lot of processes that happens before, as soil moisture or evapotranspiration, for example. And I think it would be good to see at these other variables to really better have a better representation of all these physical processes. So that's why, for example, the simulation of multi-observations could be a good approach, a good strategy. And yeah, that's my opinion.
Thank you. I think we have a signal that we need to adjourn the session
It's time
for
to
the
the
picture.
photo.
Otherwise, we'll be missing the pictures.
So
And
thank
we'll
you
be
again
Photoshop.
for our presenters and let go.
So be relaxed, not too much relaxed because we start to be relaxed. But so we can start, and then she start, right? And the first talk is from Samuel Johnston from H20 Geomatics. We're talking about the deep learning approach for lake ice cover forecasting. You should put in the presentation mode and it runs. It's kind of silly. Sure.
Okay. Hello. So hello, everybody. I'm Sam Johnston. I'm an undergrad student from Canada. I study at the University of Waterloo. Currently, I'm conducting or doing an internship with H2O Geomatics. This is some work that I started in winter of 2023 through that internship, and I'll be presenting the ongoing work today, which is not yet completed, and some results we have. It's a deep learning approach, as you can see, to ice cover forecasting. So some background. Lakes comprise a large proportion of land surface at northern latitudes, particularly in Canada, as you can see in the figure on the right. This is some water fraction coverage across Canada. This ice cover extent from lakes freezing affects the energy and water balance, both locally and regionally. And lakes provide socioeconomic benefits to the local populations. And we know that lake ice cover is a thematic product of lakes as an essential climate variable. So this sets up a need for some ice cover forecasting models that can handle data that's spatially and temporally varying. So existing ice forecasting models tend to be one-dimensional, so they consider points, not spatial interaction. And we also know there's a lack of long-term gap-free spatially varying ice cover extent data. So the existing data we have doesn't date back very far, just due to nature of remote sensing and the new products we have. So problem formulation, there's an increased number of spatial temporal observation reanalysis data just in the last 20 years. Deep learning algorithms are also quite popular at the moment and are very data hungry. And there are also existing deep learning architectures that can handle spatial temporal data. So we've figured that if we try and combine this increase in remote sensing data with deep learning algorithms, we can try and build a forecasting model to perform ice cover extent forecasting. So the data sources we're using the IMS, which is the Interactive Multi-Sensor Snow and Ice Cover dataset, which is provided by NOAA. This data set is mostly classified by analysts and comes in a number of resolutions. We're using the 4-kilometer resolution. You can see some raw data in the top left. It's in a polar stereographic projection. And all we're doing to process it is clipping to an area of interest. So moving from the figure in the top left to the bottom left. This is taking a sample from the data set over Great Slave Lake in northern Canada. The meteorological data we're using for our forcing is ERA5, specifically ERA5 land, which is 9-kilometer resolution. And we perform some processing on this data to align it with the IMS data set. Namely, we calculate an additional variable that might not be natively available if we have any of interest. We aggregate from the hourly to daily temporal resolution. IMS data comes in a daily format, and we reproject it into this polar projection and finally interpolate onto the 4-kilometer grid. And so what we're left with, what we're left with, I'll go to this slide, is a data set where the IMS data and the ERA5 data are aligned. So we can see 3 variables from our data set in the figure on the right. The top is the IMS ice cover, and the 2 following are temperature and relative humidity. And so each pixel should align across the data sets, was the goal of the processing. Just to mention briefly, we are using lake masks. These are developed from the IMS data set. So we're selecting areas of interest. These are the study sites for our study. And I've manually removed pixels that are not part of the study lake. And then in the bottom column, we're also using lake depth or bathymetry, which is provided from the paper referenced in the bottom from some colleagues who wrote this paper. So going back to the resultant data set, it spans from February 25th, 2004 until January 2022. We're using images that are 128 by 128 pixels. Each cell is 4 kilometers. It's all in this polar stereographic projection, and there's 5 study sites currently, which I've listed here. We're masking the IMS data, and the variables currently under study are just temperature, specifically 2-meter temperature, 2-meter dew point temperature, and relative humidity, which are all highly correlated. The reason for taking such a small feature set for the forcing is we wanted to start with a minimal viable product and see what these algorithms can do with a small set of variables before eventually scaling up to more variables and more features. We are also using bathymetry at the current stage. So the model overview here, this is the black box overview. Our model in the center here is taking previous ice states, a sequence of ice cover classifications from the IMS dataset, along with what I call current meteorological forcing. So this is coming from the ERA5 dataset. And what we're asking it to produce is the predicted ice cover in the subsequent sequence or window. And so, yeah, going a bit deeper, let's break this down. So the previous ice states are passed to an encoder along with the current meteorological forcing, but 2 separate encoders. And the purpose of these encoders, these convolutional neural networks, is to try and augment the feature space. And this, the idea or the intuition is to capture spatial patterns in the data set. So it does not consider any temporal interactions at this stage. And then once this feature space has been augmented, we can call this the latent space. And there we are using decoupled spatial temporal transformer blocks, which are these gray abstract blocks here. These components of the model, they attempt to combine features both across space and time. And so intuitively, you can think of them as performing the bulk forecasting task. So initially, we have these 2 blocks following the encoders. The purpose of them would be to try and capture temporal patterns in the input data, whereas the 3rd block should try and perform some type of interaction between the forcing and the previous ice cover, so performing more of the forecasting. And then finally, we finished with a CNN decoder, which takes from our latent feature space and returns it to the original feature space, so transforming from this latent space back into ice cover. So I won't go too much more into depth with the model, but talking about how we trained it. The data set, we're using a random seed for reproducibility, which was just selected randomly. I just selected a seed at the start of the work. The data set for training spans from 2004, February 25th, the start of the data set, up until 2017. So there's roughly 4 years that are left out of training. We're using inputs of 5 days and outputs of 5 days. This is what I call the window size, and there's no overlap between the days for the input and output. And we use what's called a validation data set as well, which is removed from the training data set, where 80% of the training data set is left for training and 20% is removed for validation. The way I'm doing this is illustrated in the figure on the left. We're selecting contiguous chunks of roughly 10% twice from the training data. And the purpose of this is that because we use sequences, if I were to select randomly throughout the training data, we might have overlap between the train and validation data. And so to provide a better metric of how the model is generalizing, we chose to remove contiguous chunks. And I've highlighted here as well, just for Lake Winnipeg, that for the seed we're using, by random chance, the chunk removed for validation happens to be a 20% contiguous chunk, but this is just random. So the steps for training, we're normalizing features, We do some class balancing as well, because as you can imagine, many of these lakes spend most of the year either fully ice-free or fully ice-covered. So we balance the data sets that when training, the model has more emphasis on the freeze and thaw period, so it doesn't gain bias towards fully covered or fully frozen. And we perform some hyperparameter tuning to try and optimize the model. So testing, we're using these 4 years that I mentioned that are left out. There's a gap between the training and the testing data. So the testing data starts in 2018. We perform some time stepping, so model inference, which is shown in this figure. To start, the model needs some input from IMS, after which we reuse model outputs as inputs, so time stepping. But throughout the entire long-term forecast, we use ERA5 meteorological forcing because the model is just producing ice cover. And so we do a number of forecasts. We do some multi-year ones over long periods of time, 4 years or 18 years, as well as some individual seasonal forecasts, which I'll show here. So this is for each lake. What we've done is we've performed a long-term forecast using this time stepping approach. And then what you're looking at here is the fraction of ice cover. So across the lake surface, we've taken the percent of the lake that is frozen from the model output. So in black is the IMS data, in red is the Canadian Ice Service data, which is a data set we did not train on. It's just an external additional validation data set that we're using. And then the blue is the model forecast. And so I've highlighted here 2 spots where the model is performing poorly, specifically for Lake Winnipeg. But generally, you can see that the model is capturing the seasonality of ice cover, which is quite positive. And do note as well that the model was trained to only do 5-day forecasts. So during training, the model was only ever trained to forecast 5 days in advance. And now this is testing it to do a 4-year forecast. So this is quite promising from our perspective. Going on to shorter term seasonal forecasts. These are some breakup forecasts. You can see here better, more clearly. If we look at the 2019 season for Lake Athabasca, we have these small spin-up errors. So the model is melting a bit of ice right at the start of the winter, which does not conform with what we would expect. And this seems to be a common problem we're having, at least for short-term forecasts. We sometimes have spin-up errors. But again, generally, errors are within 2 to 3 weeks, though sometimes we have larger errors, which we are not sure exactly why some years are easier than others as of yet. And similarly for freeze up, here we can see a larger error for Reindeer Lake in 2018, so far bottom left. This model attempted to try and freeze the lake far too early, so well over 4 or 5 weeks early. But again, generally errors tend to be within 2 to 3 weeks, though breakup is currently a lot better for us than freeze up. And it is also interesting to note that the IMS data, because it's produced from satellite imagery, tends to suffer a bit from cloud cover. So the IMS data, depending on the year, will have a bit more of a punctuated growth in ice, just because it depends on when they can classify the ice cover. So it's nice that we also have this Canadian Ice Service in red, because we can see for some years the trend in ice cover is actually much slower than what you would observe in the IMS data, or potentially starts earlier, ends later. So for some years, we're more correct than if we were to just look at the IMS data. So now we can also look at how the model is predicting spatially across a lake surface. So for these, how these are produced is we take the first date when a given pixel transfers from an ice classification or an ice forecast to a water forecast. And so in the top of each of these figures on the left, so top left is the true ice off, which refers to the IMS classification, and then the model's prediction on the right. And so from these, you can see that the model is predicting some spatial variation in the lake forecast, right? So it's not predicting the same date for every pixel. So this is positive, and it conforms roughly with what we would expect from the lake depth. So specifically for Great Slave Lake, at the bottom of Great Slave Lake, we know there's an inlet there, so it should be breaking up sooner than higher up in Great Slave Lake. So this is positive. And then in the bottom, I'm just plotting the difference. And so red pixels refer to the model predicting a breakup early, and blue refers to late. Similarly, for the pixel-wise freeze-up, for these, we have much more chaotic behavior, especially if you look at the far left figure for Great Bear Lake. You can see that the model's prediction is much more chaotic, but similar results in that the deeper parts of the lake should freeze up later than the shallower parts of the lake. Okay, so some limitations and conclusions. Some limitations are that small set of variables that I described we're using for forcing. So we know there's probably gains to be made in adding things like wind speed, precipitation, and cloud cover. Our approach does not consider ice thickness. This is something we can't consider because there is no spatially temporally varying ice thickness data set, but it might explain some errors in the freeze up and breakup, specifically the breakup. If you have a very cold winter, we don't have any capturing of this, larger ice thickness, which takes longer to melt. We also have some limitations in the data set. So the ERA5 variables we're using are in fact diagnostic. So they actually include the ERA5 ice model's influence. So the temperature is influenced by the ERA5's ice model. So there's some bias in that way. It's not prognostic. The IMS also has these temporal gaps, which I mentioned, and we know that the IMS data has some known artifacts or erroneous pixel classifications, as well as the bathymetry data not being perfect or conforming with reality for everywhere in the lakes, but this is a known issue with most bathymetry data sets. But our conclusions so far are that the data-driven models have the capacity to learn the relationship between climate and ice cover extent. They can learn spatial patterns across a lake of the freeze and thaw, and they can forecast over very long periods of time without significant error accumulation. So some outlook, particularly mostly outlook, because my background is less in this field, so I don't have too many recommendations. But deep learning, we know that the future work, should focus on scaling to more study areas and investigating the effect of combining these approaches with existing model approaches, physical-based approaches. Adding more sites to try and test the generalizability of these models for, global. And expanding the set of meteorological variables, drawing on existing lake ice modeling approaches, as I've mentioned. Okay, thank you very much. That's it for me.
Thanks a lot, also for being in time. We have time for questions.
If we had one missing presentation, I understand you train your system on 5-day forecast.
Yep.
And then suddenly you jump for several years forecast.
Mm-hmm.
Then you don't have any portion in the future except climate.
When I do the long-term forecasts? Yeah, that's correct. So to do the long-term forecast, you just need one window of initial ice cover. So I start from January, so it's full ice cover for all of them. And then as long as I have ERA5 or forcing data over the entire forecasting period, it'll run. Yeah.
You don't have forcing.
I do have forcing. Sorry.
January goes with the forcing in that.
Yeah. Yeah. So over the entire forecasting period, I need forcing. Yeah.
How do you do it?
This is the ERA5. This is the ERA5 data we're using as forcing. Yes, I'm not sure if I understand.
Is it for every year?
Sorry. It's not a hindcat. It's the future.
Actually forecast.
Ah, got you. Okay.
This is significant, very significant.
Okay.
You did not mention. So it's not a forecast.
Okay.
It's terminology.
Okay. Yeah. Yes. Yes. Yeah. Yep. Yeah. Yeah, this is something we'd like to do, but yeah, we're aware of this problem as well. Yeah. Yeah, and one thing we've thought of as well is some of the errors we're seeing, though we haven't tested it robustly, we do think they're consistent with the errors in the ERA5 data for their lake model, which tends to be early by roughly 2 weeks, which is similar to what errors we're seeing. So it's likely that the biases in the ERA5 data are being brought into our model. Yeah, as you mentioned.
Any other? Well, if not, we can move to the second speaker, who is Emmanuel Dutra from IPMA.
Oh, no. I think I hit the wrong thing.
ESC.
Maybe.
Oh,
I'm not
we
sure.
are on YouTube.
Here you go. No, I wasn't sure if I closed it. But it's...
Co-variability of soil moisture, vegetation, and land surface temperature from Earth
think it
observation.
should be.
Yeah.
Is it show? Okay, fine. Well, hi everyone. Good afternoon. So I'll be talking about this covariability. So we were discussing a bit how should we call this study, and covariability seemed a good option. So this link between soil moisture, vegetation status, and land surface temperature, and from an observational perspective. How do I go forwards? Yeah. Okay, so just to prepare the scene. So this is a very simple conceptual model, and that, well, I guess that everyone here in the room, this is not new. It's what models have been doing for a long time. In terms of the surface energy balance, the main difference is that here we consider only clear sky conditions, because this is when we can retrieve land surface temperature. And our model or hypothesis is that compared with a normal situation, if we have a wetter situation and also more vegetation, also implies a bit more vegetation, we would have a bit more latent heat flux and a reduction of the thermal, while on the drier conditions, we would have a reduction of evaporation with more thermal emission. And so the question that we put here is that whether we could see this blueprint of land surface temperature in this covariability of soil moisture and vegetation status. Can we observe this from the...
Just interrupt you.
Yes,
Sorry.
yes.
No, there is just a little problem because this is a PDF or a PPT?
It's a PPT.
Okay, because I cannot see on WebEx the slides, so there is.
Because it depends on the screen that is shared. I don't know, because now they are kind of...
Maybe on WebEx it's not shared anymore.
Because this one is, if you share this, it doesn't work.
No.
So it should be another screen.
No, just try.
Control P.
Yeah.
Which
Just extend.
Extend?
This is a PT. If it's a PPT, it's extend one.
But then waste it. This one. Okay. Control P. Extend. Extend is already there.
Try to now to present. I don't know what happened. No.
Maybe WebEx is not sharing
the correct screen.
Share.
Oh, sure.
Mm.
Which one? This one?
Okay.
No.
No, which one?
Yeah, it should be screen 2, yes.
Screen 2?
Screen 2.
Yeah.
Which one? Yeah.
Good.
Okay. Sorry.
No problem.
But this is not your presentation. This one. Is there?
Do you see it now?
Good.
Okay, perfect. Okay, so returning, so the question that we put forward is whether we can see this blueprint of LST in the covariability of soil moisture in vegetation status. So a bit more detailed is we will try to see if we can find when and where we can observe these strong relationships between internal variability of soil moisture, vegetation state, and land surface temperature. And a more generic, can we see this from an Earth observation perspective? Well, it is important for model evaluation and for other applications, like, for example, subseasonal predictability, where it could matter the land surface initial state. So I will mention the observations, data sets that I'll be using, starting with the spatial covariability, then interannual, and then a bit of a side note on evaluating some high resolution kilometer scale model simulations and the outlook. So the data sets, we use the Landsaf, LST. For that, I will always show only monthly means. And for that, so we compute for each grid point, the monthly mean diurnal cycle. And from there, we take the daily maximum out of the daily mean diurnal cycle. For vegetation cover for FVC, so it's a fraction of vegetation, green here between parentheses, cover. This is already a 10 daily product, and it represents a monthly mean. And for soil moisture, we use the ESA-CCI, this version 8 combined product, also monthly means. And this is already native at a 1/4 degree. The other ones, they are originally at 0.05 degrees. We aggregate to a 1/4 degree. The region is this MSG disk. So here on the 0 degrees longitude, and we have 18 years of data. So before going into internal variability, in fact, when we started this work, we just thought, well, how these things compare. So we selected, not randomly, but this is an example. If we select all the pixels here in this region, this is South Africa, and we select their summer. And this is just a simple scatter plot where we plot this distribution of the map. So the mean over those 18 years of the daily, of the LST max of the mean diurnal cycle versus the fraction of vegetation cover. This is the temperature versus the soil moisture, and this is the vegetation cover versus the soil moisture. This is just the scatter with the density and just a linear regression. So what we do find, if we select well the region and the season, a very high consistency between the land surface temperature and the vegetation and the soil moisture. And well, this is good news. It's somehow expected, but well, they are derived from very different sensors. So these data sets, they are consistent and according with our interpretation of nature. So what we did not expect, or we didn't know what to expect, is how would this relation look like? And in fact, in some of the regions, in fact, we do see a very close to linear relation between land surface temperature and FVC. The same with the land surface temperature and soil moisture, while for vegetation soil moisture, we have this a bit more non-linear kind of a square root, which is kind of expected with some kind of saturation when we go to higher amounts of vegetation. So this is just looking at a snapshot, the mean climatology over this region. But our main goal is to look into internal variability. So what we do, we compute for each grid point and for each calendar month the correlations. So the internal correlation. So we have 18 samples. The samples are not that much. So we are really in the limit of what we can do with the correlation. But so we compute this for all these three pairs: vegetation, LST, soil moisture, LST, and vegetation, soil moisture. This is just an example of how the maps look like in July. Then they are screened, so we only keep significant correlations. Then it's lots of maps, so we just compute then the maximum set of consecutive months with significant correlation. So and from there we can define a duration and a start. And this is how it looks. So in the top here you have the start, on the bottom the duration of these pairs of correlation. So for example, if the duration is a bit easier to explain maybe. So if we have here an orange color around here, it will mean that there are between 3 and 5 months of consecutive months where the correlations between the fraction of vegetation and LST max are significant. So this is, and here on the top it shows the first month, or here is the season where it starts. And so all these results are still ongoing, so we still have quite to digest here. But the first things is that, so we think that we can take these maps, that they will resume this when and where this internal variability between vegetation and soil moisture and land surface temperature matter from a surface energy balance perspective. So another thing is that these they are quite consistent, at least, well, I'm sure that for you guys looking from there, the maps, they look quite similar. Of course, there are some small spatial details, especially in the start. But generally they are quite similar. And then, of course, well, then another question that is raised after this is why? Well, why these regions and the seasons of start? So, of course, it has to be related with land cover and climate and seasonality of that region. So as an attempt to check this and to quantify, so this is a map of low vegetation cover that is used by the ESA-ESRIN model, for example, but it's based on ESA-CCI. And so, of course, very quickly, we can see that there is a very good, just by eye, the places where we have high durations. This is for vegetation and land surface temperature. They map quite well with areas of mostly dominated by low vegetation. And this is just a box plot where we see the distribution of all these pixels. So, and we see that they are mostly dominated by low vegetation pixels, the coverage of each pixel, while the high vegetation is much lower. So, of course, what we have now is that this signal is mostly present in regions dominated by low vegetation. This is also not completely unexpected. So one of the things to have, because we are looking at correlation, so we need to have variability. Of course, that in the deserts, there is no variability. And in fact, also in the tropical regions, there is not that much variability of vegetation. So the correlation will not show any signal. So this somehow explains that. On where we can find this tight link between the surface conditions as seen from Earth observations, and the same with land surface temperature. Now, the next steps ongoing, and I was hoping that I would have something to show today, but it's not ready yet. In fact, is now to use this type of diagnostics to compare, to validate or evaluate models. So this is it's what is ongoing now, and we are starting with the reanalysis. So, but unfortunately, I don't have those results to show you today. But on a following, or not following, but on a similar topic, this idea of using Earth observations, and here is within the framework of this EU projects, Next GEMS, that is working on a new generation of storm resolving Earth system models. So having global Earth system models running at rather high resolution of the order of 4 kilometers. And there are two models here. It's the ESA-ESRIN IFS and ICON. And of course, this puts here a question, many questions, but for example, how do we assess the realism or the quality of these models? And in fact, again, well, land surface temperature could be a good candidate because we have rather high resolution data. So this is an example where, well, you recognize this region for the European people. So this here is Switzerland. So if we take, this is for June, July, August, the daily LST mean, so the minimum temperature of the mean diurnal cycle for June, July, August for a 5-year period, I'm not mentioning here. And this is on a resolution of about 5 kilometers. And then if we take the mean of this field, and it just showed the anomalies. And here on the top, we have the IFS, so ESA-ESRIN simulations at 28 kilometers, at 9 kilometers, then at 4 kilometers. This is ICON, we only have one at 4 kilometers, and the observations from the satellite product. So, well, we can see some features like the Paris Heat Island, because this is mostly its minimum temperature, so we see that signal there. We also see the lakes in Switzerland, and we do see that visually the model, especially at high resolution, especially the lakes, they are quite well represented. The city a little bit, because there is also urban scheme in the IFS, but not ICON because it does not have a urban scheme. So, And also this spatial pattern here is tightly linked with the land cover here in France, that I don't have here the map, but we can also see this imprint of land surface temperature on the land cover. And this is just a scatter plot where we also see that, and this now is for the daily maximum temperature. So we do see that, and this is known, there is a generic underestimation, a bias in the model, independently of the resolution that is running. But what we do see is when we increase the resolution in the model, the bias is still there. It's due to other reasons, but the relation starts to be a bit more linear. So it's also good news that we can also see that the model becomes much closer to what the satellite brings. And another thing that we can also do with this, also because these model simulations, they are global. Because of course, what I showed before, it could have been done in the past and still nowadays with regional climate simulations. So, but from a land perspective, what we have is the same model with a very high resolution. If we manage to handle all the data. And so a question that we've put is that if we think about subgrid scale variability, for example, if we have models running at a 1/4 degree, like the reanalysis, they don't resolve, or they try to resolve, for example, some models with a tiling approach, that subgrid scale variability. But now that we have the satellite observations and the models running at around 4 kilometers, if we course that data into a 1/4 degree, for example, we can compute a standard deviation as a proxy for the subgrid scale variability, which is resolved in these storm resolving models. And let's see how do they perform. So this is for what it gets when you look at the satellite product, Landsat. And this, I don't have it here, but this is for June, July. It's not written here, but it's June, July, August for the daily maximum. And so all these areas here means that there is more subgrid scale variability. And of course, that this will be due to many factors, but this is how the model simulations look from the IFS at 4 and 9 kilometers, in the ICON at 4. And here, this is a scatter plot of all these when we put the Earth observations versus the model simulations. And well, what we do see is that while ICON has some tendency to underestimate this, one of the reasons is that, in fact, it does not have I don't want to say proper, or it does not have a skin layer to solve the energy budget. So in fact, it uses the soil temperature of the first layer. So it has a bit more, it takes a bit more to respond. It has more thermal inertia, so it does not have a pure skin layer. So that partially explains this, and also some biases on the daily maximum. But the IFS has, and in fact, we do see the added value of going higher resolution, where it has a rather good match in resolving this subgrid scale variability. And while this is due mostly to topography, of course, while we can see the mountain chains, but also land cover. For example, here in all this region here in Brazil, there is also some topography variability there, but it's mostly land cover changes, and they are very difficult also to model. But we see this signal in the satellite, and we see that when the model runs in a high resolution, also has that. So, and this is my final slide. So coming to the first questions we've put, can we derive this type of information from observations? Yes. The when and where we have these strong relationships, the first results, they show that it's mostly dominated by mostly in low vegetation regions, and the season that matters most is mostly the transition period. So, of course, while this is not completely new, so we would kind of expect this to be, so it's good. So in one hand, it's good that we can see this in the observations and quantify. And one of the things is now to apply these diagnostics to the models, but it also means that these are the regions where we could play a bit more, focus a bit more attention in how the models are representing these processes. So that this bare ground to low vegetation and transition period is really the critical point where we do see that the surface energy balance clearly reflects the land surface state. So for this next generation high resolution models, and we've heard a lot in this conference about all the digital twins, and this has a big push in Europe with Destination Earth, so it's happening. And in fact, And here, well, Earth observations play a fundamental role because without that, it's the only way to assess the realism of these models is with high resolution Earth observations, because without that, it's really very difficult to assess. In terms of recommendations, so for this type of study, so globally consistent Earth observations data records. So for example, as I showed you here in all these analyses, I was just looking at the MSG disk because this is where we have the data, so we don't have it on the other ones, and consistently of these three and other variables. So this is very important. When we look at these longer time periods, the resolution is not so crucial. So of the order of 25 kilometers, we feel that that's okay. But now when we go for these very high resolution models, then we need high resolution Earth observations. Those become very important. But then on the other hand, at least at this stage, we don't need, and it also doesn't exist, but we don't need a long time period. So we are not yet looking at internal variability of these very high resolution models. We just want to check that their mean climate is reasonable. So when we go for high resolution, a few years would be enough to go with this kind of studies. So that's it. Thank you.
Thank you very much. Any question for Emmanuel?
Thanks for the talk, Emmanuel. I have one question on your first part of the talk. To which extent is the use of land surface temperature and vegetation in the retrieval of soil moisture, how is that clouding your results? Because the soil moisture retrievals, they use ancillary information on temperature and vegetation. So how is that now influencing your results?
That's a good question, but I'm not sure this particular product, how much information.
So it's the combined TTI product.
Yes, so I don't know.
The passive microwave, I'm sure this.
If there is someone here that can.
Yeah, the passive microwave uses land surface temperatures in the LPRM model to separate the vegetation.
But microwave.
Yeah. Yeah.
Still LSD for
KU band. Yeah. No, in the soil moisture, the passive microwave soil moisture retrieval, the land parameter retrieval model from VU Amsterdam and NASA, it uses passive microwave land surface temperature data in the model. So it is a model input indeed. Yeah.
So, but it's the passive, it's a microwave temperature, not the thermal.
Yeah, it's microwave temperature.
So in that sense,
Yeah.
yes. So yeah. But the vegetation of the microwave. So they are for this vegetation product we are using in the LSC, there is some because the land surface temperature depends on, for the emissivity, it depends on that vegetation. There is some link, but not. But there, yeah, I would say that soil moisture is quite independent from this for the temperature.
Yeah. I would have a note on that as well, because I thought, what was the reason for choosing the ESA-CCI soil moisture data set where you're using all the soft products, all the land soft products? So why not use the HSOF 12.5 kilometer soil moisture, which doesn't use any vegetation data or temperature data in it? It would be more independent and closer to the resolution that you have from the LSAF products as well.
That's a good question, and I don't know if it was available for this temporal extent since
Yeah, it's
2004.
from 2007, it's available.
Okay, and it's also fully independent, so it's also okay. Well, it's also
more
something to
independent
consider.
than the passive microwave product, I think.
Okay.
Yeah.
Maybe one note on that.
Yeah, sure.
Once independent on like the center of errors and all like physical independence. But not formulated error. I also think that depends on
Mhm.
Dependency versus consistency, one of the challenge. Actually, in my talk, one of the challenge in all this kind of analysis is always the same. When you use different data set, we should take care of what we are looking at. Any other question, comments?
Just going on the use leader, right? It's the other digital information, for example.
Oh, sorry. Yeah, that was whether you use other metrics also, like mutual information.
No. So for now, it was very simple. It was just the linear correlation. Yes. So for sure that there are there could be different ways of looking into this. Yeah, for sure. Yes. And we are welcome to your opinions and suggestions, in fact. So.
Any other? If not, thank you very much. We can move to the fourth speaker.
And the fourth speaker should be Simone.
Yeah, right.
It's towards the digital twin of the water cycle in the Mediterranean basin. So the speaker is not Lorenzo as it.
Yeah, I'm not Lorenzo. Yeah, he cannot be here. So good afternoon. What I will show in the presentation today are some of the results that we achieve in some project funded by ESA. The first one is the Digital Twin Earth hydrology product, whose goal was to develop and demonstrate a prototype for the Digital Twin Earth with a focus on the water cycles. In particular, we aim to, let's say, highlight and test the potential of high-resolution satellite product for describing the hydrological cycle. We implement the continuum hydrological model. Is a model developed by Human Research Foundation. It's a fully distributed one. It solves the energy and mass balance on a regular grid that can be set from few meters up to several kilometers. It provides the temporal and special evolution of, say, classical hydrological state variable, discharge, soil moisture, snow water equivalent, land surface temperature, and evapotranspiration. We were interested in, say, testing the model in this context, testing the Earth observation that drive the model in the Digital Twin Earth context, because it's also an operational model used by for example, in Italy by national authorities for forecasting, and also in several countries around the world for mailing for flood forecasting, and especially in Africa and South America and data scarce environments. So the estimation of precipitation is one of the main challenge to have a robust forecast. But anyway, in the context of DTA hydrology, we test the study area was the Po Basin. We already had in those days several presentations that illustrate very interesting research activity in the Po Basin, that is very important from Italian economy. Is one of the main industrial area in Italy, with more or less the 30% of agricultural national production that derived from this area, and 20% of the population live here. So it spans from the Adriatic Sea up to the mountains, more than 3,000-4,000 meters above sea level. It's very well instrumented. We have more than 1,000 rain gauges and temperature sensor, a lot of ground station, about 170 snow depth station, and 27 river gauges. It's, of course, very affected by human activities. 99 dams are here, and we have also three major lakes. The studied period is a 3 years period from 17 to 19.
And within the DTA context, we test several high-resolution data sets that were produced by the partner of the project, in particular, 1 kilometer soil moisture product from TU Vienna, 1 kilometer evapotranspiration product GLIM from Ghent University, high-resolution 1 kilometer hourly precipitation from ERP-CNR and also discharge from satellite from ERP-CNR. We also use the available sea snow 1 kilometer snow depth data set, and we perform several experiments. Some of those high-resolution satellite variable data were assimilated into the model. Some were used as input, like soil moisture and terrain, so the high-resolution precipitation data set. We switch off the hydrological balance, the energy balance in the hydrological model, and we use GLIM as input, and we test also the calibration of the model using a satellite discharge. On this figure, you can see the performances of the hydrological simulation in terms of KGE. We consider a baseline, that is the run of the model with the ground observation. Since the time window is only of 3 years, we split the, we consider some of the gauging station for calibration and some for validation. Then in the baseline experiments, we also assimilated snow depth ground measurements. So the results in terms of KGA are pretty good, both for calibration and validation station. Then we perform a set of experiments using satellite data. We use soil moisture and terrain GLIM as input. We assimilate sea snow depth. We assimilate the soil moisture, 1 kilometer product, and then we perform a run of the hydrological modeling, considering all the satellite input. What we can, this is black line is the no skill threshold, considering the KGA value. So first of all, we have a skillful reconstruction of the river discharge for all the experiments. That's one of the first, let's say, good results. We see that simulation, including the use of GLIM and the assimilation of snow depth from sea snow, slightly improved the baseline run. I think that it's particularly interesting also from the snow point of view. Let's say these products produce an increase of the assimilation of this product produce an increase in the model performances. So it's slightly better than the simulation of the snow depth ground measurement. When we consider all the high-resolution satellite data as input or assimilated into the model, we have a slightly deterioration of the mean performances of the model, but so the performances are still good, and this run generates the best performances in the non-calibrated station. This was another, I'd say, interesting results. In another set of experiments, we used soil moisture, terrain, and GLIM as input. In particular, I would like to highlight the last one, in which we used those 2 variables as input for the hydrological modeling, and we recalibrate the model, not using the observed discharge, the ground observed discharge, but using the satellite, the discharge estimated from satellite. So even in this case, the performances of the simulation were good. So if you want more detail, there is published paper on that. As a first conclusion of this part, we can see that the hydrological simulation driven by different combination of high resolution satellite data set produced encouraging results. More or less all the analyzed river station are above the non-scale threshold. We saw that satellite precipitation, as expected, has the large impact on the model performances. And as I mentioned, we have a skillful reconstruction of the observed discharge or running the model forced by high resolution satellite product. Then in other two projects for demand and DTA hydrology evolution, we try to upscale the result that we obtain in the Po Basin at the Mediterranean scale, so a much wider scale. And so we implemented the hydrological model on whole the Mediterranean basin. We implemented the model on APC, high performance computer that was made available by ESA in the cloud. We separated the Mediterranean area in 28 hydrologically consistent domain. The data for the calibration of the model were available only on 5 basins: Megerda Basin in North Africa, of course the Po, Herald Basin, and Hebro. As I mentioned, the model was implemented on APC using virtualization of modeling using a Docker framework. So the cloud was not such a big infrastructure. 80 cores were available, but the interesting thing is that it can be scaled to bigger machine. The implementation at the Mediterranean scale include several dams, 186 dams with the minimum volume threshold of 100 million of cubic meters and 52 lakes. So these infrastructures have been considered in the modeling framework. Of course, one of the main problem is that we do not know the real maneuvers operated on the dams. As input for the hydrological modeling, we use the high resolution of 1 kilometer resolution precipitation with hourly resolution estimated by the integration of GPM, so in moisture to rain scan and CPC. So this product was already presented during previous session. And as I mentioned, we calibrate the model on the 5 basins where river gauges, where observation from river gauges were available. We have a calibration period of 2 years and a 4-year validation period. The results of this calibration show that we have, say, good performances on Herald Basin and the Po Basin. Of course, the validation KG is slightly lower. And we have poor performance in the Hebro and especially in the Megerda Basin. So the Megerda Basin saw the largest difference between calibration and validation results, with likely this, say, poor performances in North Africa are due to the challenges of estimating precipitation in very dry area, and also the quality of some of the discharge observation were not so high. While on Hebrew Basin, the suboptimal scale are mostly due to the impact of the dams that are in the basin. So the basin is heavily affected by the maneuvers operating for hydroelectric production, as reported in say other literature, especially for the calibration of European flood awareness system. Well, the same problem was mentioned. But in general, we are quite satisfied with the performances of the model, driven by the high resolution Earth observation dataset. As last, say, experiment within the context of DTA hydrology evolution, we study the event that affected many Mediterranean countries at the end of October 2021, the Mediterranean hurricane named Apollo. Unfortunately, 7 people died during this event. In particular, we study the impact of the event on the Sicily island. You can see here the cumulated precipitation estimated from ground station and radar that impact the region. More than 400 millimeters of rainfall in those areas around the city of Catania. In particular, here there is the Catania floodplain that is very important area for the agricultural production of the island. As you can see, the effect was heavy. And we perform a long-term hydrological run for the Sicily. We don't have observed discharge in this area. So we create a baseline. The baseline was the run of the model driven by the ground observation. So you can see here in Catania floodplain, the discharge peak due caused by the Apollo Hurricane. And then we ran the model using the high resolution Earth observation precipitation. We saw that in general, the simulation driven by satellite precipitation has a negative bias and underestimate the flood peak. And then as a further comparison, we use the ERA5 data to run the model. In this case, ERA5 has general positive bias, but underestimate again the peak of the discharge. So the simulation driven by Earth observation precipitation outperforms those forced by ERA5 more or less in all the region. Since we don't have, let's say, ground discharge observation, we say test the performances of the result of the model driven by satellite observation using say the flooded areas. In this picture, you can see the flooded area estimated from Sentinel by the Outwit algorithm. Yesterday, there was a presentation of my colleague, Luca Pulvirenti, that showed the details of this algorithm. And we coupled the hydrological model with the bidimensional hydraulic model, Telemac, again, developed on the APC using a high resolution DTM, a 2-meter DTM. So these were the flooded area and the maximum water depth estimated by the modeling chain that use ground station data to feed the hydrological model and coupled with the hydraulic model. As you can see, of course, there are differences. I think that the Sentinel maps, it's not the absolute true. This was a flash flood, so the passage was not, satellite was not synchronous with the flooding peak. We saw in particular an underestimation of the modeling chain in this part. The flooding here was caused by a very small drainage network for irrigation that are not even seen by the 2 meters digital elevation model. And when we force the modeling chain with the Earth observed precipitation data, we obtain this map. So there is a flooding lower in terms of extension and depth respect to the modeling chain driven by ground observation. So we compare the maps, so the observed from satellite maps and the simulated maps, and we obtain a critical success index of 0.35 and 0.28 in this with the second modeling chain. So we think that's quite good results. As a conclusion of this second part, so we successfully implemented in the context of DTA the hydrological model on APC infrastructure for all the Mediterranean basin, and the results of this simulation fed the digital twin platform that Luca showed at the beginning of the conference. And we can also say that the simulation driven by the high resolution satellite precipitation producing the very, let's say, quite good results in the Mediterranean basin. And for the test case of Sicily, they outperform the simulation with ERA 5. And also the results with the complete chain with an hydrological model plus an hydraulic model leads to a good representation of the observed inundation extents, especially near the main river network. As a small recommendation from my perspective is that, so they think they are in line what we saw in this conference and with the goal of that ESA is yet pursuing. So we especially have to concentrate the efforts in developing high resolution precipitation and snow water equivalent or snow depth data set, focusing in particular on frequency, because for hydrological application we need at least sub-daily frequencies, and of course latency when we move to operational hydrology. The latency is a very important parameter. And of course for unengaged area, we have to improve the discharge estimation from EHO, as I show you in the first experiment in the Po Basin. The calibration of the model with those information leads to good results. The last recommendation in my experience and in the experience that we have at CIMA is that, let's say, we look at Earth observation data to, say, improve our knowledge on the impact of the anthropogenic, of the human on the water cycle. And particularly, we saw the effect of the maneuver of dams that usually are completely unknown. So try to understand, infer these the maneuver on hydropower plants from satellite will, I think, will help in improving hydrological the performance of hydrological simulation. So that's all from my stuff.
Thank you, Simone. We have almost closed the gap from the missing presentation. Are there still any questions for Simone? I may throw something at you then, but it's also for the next speaker on digital twins. Why do we make a digital twin? Why do we call it a digital twin? And why don't we call it a simple reconstruction, reanalysis? What do you want to achieve with a twin?
Yeah, I think that this can be a part, what I show is can be a part of the twin. So the coupling of physical model with Earth observation data. Let's say they can be, let's say, a part. Another part is the possibility for the user to interact with the results and let's say acquire knowledge in using those kind of results. So this, in my opinion, was a contribution to achieve these greater, let's say, objectives. So include those results in a platform that allow a user to see the results and interact with them is so it will be a more complete twin. I agree that this is an effort to try to improve the combination between physical model and data, but it's not really a twin.
It's not that you can do some experiment on the twin, right? It's just you have a data set and that's it. It's not you can change precipitation or something.
Yeah.
Which is what we do, like twins in data simulation. Or so then you have a twin to just do experiments with a twin rather than with the real Earth.
Yeah,
yeah. It's just more a philosophical question. Thank you very much. The next speaker is also about digital twins, so that's why I came up with the question. It's towards a digital twin for the Alps, and the speaker is Luca Brocca.
Good afternoon, everybody. If you're here from the beginning as myself, I will start and close the conference. And I saw, no, who is here? Diego, you were here, no? At the beginning? No. Wolfgang was here. So take care. So this presentation, the title is Toward the Digital Twin for the Alps. And I'm giving this presentation on behalf of Stefania, who is not here, Camici, and on behalf also of the whole team of this project, in which we work together with Synergize, with MobiGIS, and also Terranum and CNRS, and of course also ESA. How does it look like this? Okay. Why digital twin for the Alps? The overall initiative is called Destination Earth. The main point of the digital twin is not the modeling, is not the integration of modeling and observation is there, but the main point is the interaction. The idea is to try to develop something in which the user, that can be also everybody, politicians, not only scientists, but everybody can interact with the system. So in principle, a user can be able to use the model, whatever he is, and make simulation by himself to actually get the season. This is the overall idea. ESA launched something like, and actually is going to launch basically what is called the ESA Digital Twin Earth program. That basically the idea is to develop components to be ingested in Destination Earth in the second part, but the main idea is to try to assess, to understand the user of Earth, how to maximize, how to capitalize all the effort made in Earth observation to be included in the digital twin. And also it's mostly scientific driven. It's not really an operational driven activities. Then ESA has also these regional initiatives, like we have seen also 4D methodology is a kind of a regional initiative, like also the one in the Balkans. And so this one, Digital Twin Alps is here. It's a regional initiative over the Alps, and that basically is in this path. The timeline of the project was kind of 15 months. And the two main goals is to provide a scientific and technical roadmap. Basically, the project was really a prototype, a demonstration project to provide a roadmap for future development of digital twin components, the one that I have already just mentioned, and demonstrate how Earth observation and the state-of-the-art modeling, supported also by AI, can be used to improve decision-making over the Alps. The legacy is, of course, from the previous project from ESA. Also, there are a couple of projects for mostly dedicated to snow. No, there is one mostly dedicated to snow. There is another one dedicated to landslides. Then we have our DT hydrology and 4D hydrology project. And this is the main objective of digital twin Alps. So the point here, okay, technically this is how it works. But why a digital twin for the Alps? Because actually the Alps is a very complex system, and we need actually something very different with respect to performing. The Alps are part of the Po Valley. So basically we are already running the digital twin for the Alps in the digital twin hydrology project. So why this project? Because actually we are here looking at very specific condition and application that we have on the Alps. And again, the idea is always the same, to integrate Earth observation and modeling as best as we can. And here on the right, you can see all the products that have been developed during this 15 months project. And on top, you can see the one related to terrain motion, shallow landslide, and also glacier motion and deep-seated landslide. I will not talk about that. And on the bottom, you can see the one related to water, so water discharge, water rates, sand moisture and drought monitoring, flooding, and the snow water. It's snow cover, but also snow water equivalent. This is the Alps. These are the Alps. And as you can see, there are some specific study area. There is a platform because, of course, you can do a project without the platform now. But it's a platform because actually we want to show to the people the activities done. And the platform is good because, for instance, you can access the data without downloading the data. You can perform some analysis on the fly. You can access long-term data sets. We have a couple of interactive simulation tools because one other point of the digital twin is this famous what-if scenario. And we have also developed two what-if scenario also here. I will talk about that later. And all the data are freely accessible, and you can access them, you can download. Here is the quick QR code if you want to go to the, but also on the top you can see the website. What is inside? A bit more in details. So we have Earth observation data. We have in situ data, modeled data, forecast, particularly for landslides, and scenario tools. Everything in one platform. That it means that actually the platform, sometimes it works very nicely, sometimes not. Because one of the problems actually is really how to optimize this platform to make them really usable by anybody. If you want to put everything in one platform, it doesn't work too much. But in this, the ESA wanted everything, and we put there. Some example of what is there. For instance, forecast of shallow landslides runout areas. So basically, this system actually is operational and run with the meteorological forecast also in real time. And so basically, you can find on the platform in the basin, in the part on the I don't remember probably in the western part of the Alps, you can really make a forecast of the shallow landslides. There is also glacier motion. I don't know nothing about that, so don't ask me anything about that. There are landslides susceptibility maps. Again, at high resolution. High resolution means a kilometer scale. For some case studies, we have also the landslide. In this case, is the displacement as to the horizontal displacement. And for water resource management, I will go more in details here. This is at the beginning just a kind of description. We have a snow water equivalent, our river discharge, you have already saw. Daily soil moisture from different sources, from modeling, from one model and from one satellite, I guess. And for evaporation, the same. We have a satellite evaporation and also model evaporation. Let's talk of something more interesting. You know, you can go to the platform and you can see everything. Drought monitoring over the Alps, but actually in general. And the drought is a complex phenomenon, no? It's, if you are here from the beginning, actually, you probably have shown already this. Typically, we make a kind of a drought assessment with precipitation and evaporation data. Mostly in the past, now actually it's a bit less, but the standardized precipitation index was the most used index. In operationally, everybody is using still SPI. And but you have to understand that precipitation and evaporation, that they were used because they were available for a long time. They are fluxes, though they are not storage. If we have to understand the drought, probably it's not the fluxes that should be considered, because fluxes is a proxy of the storage. But the storage were not available up to the availability of Earth observation, but now we have the data of storage. So basically, change your everything that you are doing for drought, stop to use any kind of fluxes, and try to use the storage because they are available. Or at least try to test what does it mean. And particularly over the Alps, for instance, snow availability means that if you have a deficit of snow now, it means that it has an impact from 3 to 6 months from now. If you have a storage anomalies, depends on how much the storage is, but can be 1 to 2 months ahead. River surface water anomalies can have an impact on really 15 days. So knowing where the deficit is tells you when and where the water will be available. This is just an example for end of May 2020. The data, for instance, you can look in the platform. There are you don't see because they are too small, but there are 5 maps showing deficit in soil moisture from the model and from the satellite, deficit in precipitation, and deficit in evaporation from the model and from the satellite. And so, for instance, particularly in this case, there is no deficit for soil moisture and evaporation, but there is a deficit for snow. So I could expect that in June and July, there will be some water. June probably, but for the deficit in snow, probably it's very likely that you will have some issues in this basin for that year, 2020, in the summertime because of the deficit of snow. And if you have the information divided by the different parts, you can make this decision. Otherwise, not. In the platform, you can also visualize the time series. You can also, for instance, we are trying to assess what is the agreement between, for instance, model and satellite, between soil moisture anomalies and evaporation anomalies, and precipitation anomalies, and you can explore by yourself also in the platform. In the platform, we have snow over the whole Alps up to 2022, I guess. And for instance, these 2 maps is the anomaly of snow water equivalent in 2022 and the previous year, so 2021. And you can really see the difference. The blue one is with the 2021, the white one is 2022. And so you can really see the amount of deficit that we had last year. Everybody knows probably of the strong deficit, of the strong drought affecting northern Italy last year. 10 minutes, I have plenty of time. And here you can see also the time series. From one, Sarah is here. Oh, Sarah is not looking. I don't know if there is average of the whole basin or if some particular area or some particular point. But you remember? No, no problem. But in any case, here you can really appreciate the differences, quantitative differences between the two, the simulation, and you can appreciate. You can go on the map, and you can click, and you can see the data. Then we have what if scenario. 2 what if scenario, one for drought and one for flood, for sure. And for drought, we have done this kind of experiment in the Sarka Basin. And basically, the MobiGIS guys mostly, they ran the model that was developed for this basin by using different scenarios. So different scenarios in terms of soil moisture, precipitation, but also freezing level. That is particularly important for the Alps, and in principle also the human intervention. But actually, at the end, we didn't implement. And for instance, again, what is the impact of the availability of snow water equivalent for summertime river discharge? And the maps show the data from color from red to blue. You can go in the platform, and in the website there is also a text. There are also some web page in which actually help you to explore the scenario, because it's cannot be so intuitive at the beginning. We should be honest. And in this case, low precipitation scenario, and then you can see on the map the distribution. This is the river, and so the distribution along the river of the deficit. And finally, what is scenario for flooding? And so, for instance, I have the video, and I have time because 12 minutes. Oof. So, for instance, here you can go in the platform. You can select. You can play around with 3 different condition in terms of return period of precipitation, in terms of freezing layer, and in terms of soil moisture. And basically, you pick up. You click on how to compare, and then what happens that in the platform you can see 2 maps, and you can compare the 2 maps. You can compare the flooded area depending on the different condition, and so you can appreciate, for instance, what is the impact of high or low soil moisture, how it impacts the estimation of flooded area with respect to, for instance, the freezing layer, and also the precipitation. And this is the flooded map. Actually, this flooded area was done by with the hydraulic model at meter resolution, and so actually you can really see also the flooded area within the city. That is actually is a very small town. This is my final slide. Plenty of time. What's very important for us and for ESA here, and generally for the digital twin, is feedbacks. If you have time and if you want to learn to play around with something, you can go in the platform. You can give feedback to the platform to actually what is working and what is not working, what should be improved, what is missing, or whatever. And taking in mind that this particular activity actually basically is mostly addressing the problems that we have over the Alps that are quite different from the problem that we could have over, for instance, a large basin. So, for instance, the high resolution here over the Alps is not a question if we need or not. It's mandatory. Without high resolution data, you can't do anything. We have started developing this high resolution data, and so actually now, but only now, we can start doing something from in this direction. And so actually, we are really at the very, very, very beginning. Thank you very much for your attention. Finished.
Thank you, Luca. Are there any questions?
The logic of digital twins. What are the target users? They can be, of course, the public administration or the I don't know. Do you have any info about the target user that you're looking for?
In principle, everybody, from the policy makers to the stakeholders involved in the different compartment, whatever authorities, because now, of course, we are talking about water cycle, but actually digital twin should be for everything. Water cycle, carbon cycle, forest, ocean, polar, whatever. And so all basically the authorities making decision on anything. I know the guys that should work on water resource management and flood and landslide risk, but these are target users. But in principle, at least from the European Commission, Destination Earth is also for the citizens. So it's also for, I don't know, my mother that is not here anymore.
Any other questions?
Whole day of conferences, yeah.
Do you plan to assimilate sea snow data at some point, or no assimilation in this system?
It depends on who is going to make some. I believe that assimilation and integration of snow into the model is something that is mandatory over HALPS, but it depends on the partner working on it.
Sure.
The portal and well, you also said that all projects have portals, and it's quite a, so what is your feeling on this particular project, on the effort that was put into creating a portal? And many different projects create different portals, and is it really useful to have so many different ways of accessing the data? And
But then, on the other hand, there is now a huge initiative from ESA that they create something called the DESP, but I don't know anything. I know, and they want to put everything there, and so it doesn't work again. So probably we should make kind of portal dedicated for application, and that could be something more clever. But that's my personal opinion, so I don't know. But for sure, a portal for everything is not. The portal already for if you want to go in a portal for getting the data or for looking at results should be different. The data infrastructure behind that should be completely different. Otherwise, it doesn't work. If you want to make both of them, it doesn't work. At least for my experience so far. But if you try to, for instance, to differentiate, and if you try to make some clever way of showing the results, but it's dedicated portal. The portal for showing the results shouldn't be the same portal that to be used for data extraction or also for data manipulation online or something like this. I don't know, probably there are some very clever informatic people who is able to do everything all together, but.
I think I saw one more, yeah.
Do you have also data storage change in reservoir there? Or?
No, but it's something that we are trying very likely. There will be a future initiative in this framework. And one of the things that we want to do, because as Simone said before, the human impact on the water cycle is important. The two main things that you can do by satellites is one is irrigation and the other one is reservoir water level and volume by, for instance, radar altimetry, but not only. And we would like, for the first one, we are already working on it for irrigation. For the second one, actually, we would like to start.
It would be very useful. And do you have in situ data in all reservoir?
You say in Italy, yes. Somewhere else, I don't know. In Africa, I don't know.
This is what is the other question. What are the Alps? Is the Alps, I mean, it's not only Italy, it's also for Germany also. The definition of Alps is until which height?
Which height?
Yeah, I mean, the mountain are until 300 meters or 500 or where do you stop?
In terms of the lower one,
yeah,
the lower
mass.
limb. I was talking to the upper.
No, because I
have no idea.
Because I tried here now, and it seems in some places some lake are cut in two. So therefore, yeah.
I don't know where I don't know who made the blue shape file. I don't know.
Okay, so we will look perhaps.
Thank you very much. I think Luca can now start with the seat questions once again.
We have a kind of 20 minutes. Actually, if we finish a bit before, it's not a problem, particularly for me. No, but because actually, yeah, it's. How many times did you see seed question this week? Okay. And yeah, they asked us, prepare some seed question. That's something that we are working on. Don't read too much everything, but basically the first one is how to improve the water cycle. We should have better model, better satellite. High resolution and modeling, this is kind of now I'm always talking about high resolution, probably I'm kind to be crazy, but the reliability of this data is really, I like a lot of the presentation by Emmanuel, I told you by name, I don't know, by Emmanuel Dutra, because actually how to assess the quality of modeling at high resolution, yeah, to me the only way is Earth observation. But then on the other hand, we should try to find a way to assess that observation, particularly if we go at high resolution for some of the variable like moisture and evap, we are still very far from understanding anything to me. And then how to use that observation in conjunction with modeling. There is also a provocative question at the end. So what we can learn from Earth observation for improved physically based modeling, but then should we use still will need physically based model anymore? My answer is yes, but you know, there is also all this machine learning. You want to say something? But actually, we can discuss whatever you want. How was the dinner yesterday or something? I don't know.
Thanks, Luca. A couple of things, actually. Having sat in on quite a few sessions this week, I noticed that when there's talk about water cycle, then nobody's talking about the energy part. And I think that's one part that I think deserves more attention. I don't think you can separate those two, certainly if you want to have a consistent view of how things change and how the processes go. So that's one remark. The second one, I agree that currently our models are outstripping basically our observations and certainly our in situ observations. And how we're going to deal with that is actually a very fundamental question. And there is not a singular answer to that one. But that comes actually to the last one. Do we need physically based models? Yes, we do, because otherwise we don't know what we're looking at. And hence we do not know how to interpret our observations. So even though I'm really like machine learning or complex ways of data analysis, you need a physical interpretation. So there is no escaping that. So I will leave it at that. But I think the main thing, certainly as a GeoX representative, is we cannot see water without the energy part. And I think that's one thing that I've really been lacking this week, is that we have a bunch of other satellites and observations that we can use to constrain our other observations. And I would really suggest this community to look into that, because I think that's a missed opportunity otherwise. There is much more than like Sure, absolutely. Yeah. Yeah, and it connects to the carbon cycle. And that's the other part, right? And it can take the vegetation into account. So exactly that's the point, is that you go to the one and then can add another one. But also precipitation can, for instance, be expressed both in energy terms as in water terms. And there are really a lot of ways to play with that. And I think that's an opportunity I didn't see a lot of this week. That was basically my observation.
No, they get that, yeah. No, but
I want to challenge Peter a little bit. I agree that the models are very good, but they're also good because they behave predictably. So they show what we want them to show. And I often wonder what the information content is and how can we actually quantify information content. So where does it come from? What's really characterizing the real surface? So what I'm at the moment, I feel that we lack a framework for quantifying the real information content. What's the spatial resolution of the processes, both temporal, spatially? So we need a theory for this.
Could not agree more. And that's basically, when I say outstripping observations, it doesn't mean that the models are doing better than the observation. It just means that the resolution we are now looking at the Earth it seems in better detail than our in situ observation, for example. But what is correct? What's in physical terms?
It's really very difficult to say, yeah. Mm. So we need an information theory.
we need the integration of communities. Actually, we are not talking about energy cycle, but the carbon cycle is completely out. But you know, I am a hydrologist, I should consider energy, carbon, then the land surface modeling community basically don't consider river. Basically, it's everything is vertical. Hydrologic community, they consider the energy. Atmospheric community doesn't consider land. But it's a simplification that we do for doing our model, I guess. But of course, integration. Yeah, for me, at observation actually can be a kind of way of integration, because but still, there is a need of an effort that is not a single community that can be done.
Absolutely true. And I was not saying that everybody should do everything. It's like claiming that our models can do everything. I think that's one of the things that with the digital twins, I think that's a danger, is that I question a lot of times when you put in these complex modeling systems that people do not understand who use the data, what the constraints are. And in particular, when you go to climate projections, which scenarios have been used? What are the conditions for that? Does it make any sense? It requires actually quite a lot of knowledge, not just data and information, but knowledge and experience to really interpret that correctly. So I think we're really at the boundary, at the start here of how do we deal with the amount of information and data we have and make sense of it, but also have our policymakers and users make sense of it in an appropriate way. And that's going to be a really difficult challenge.
I would like to share some thoughts regarding number 1 and number 3. And I understand that number 1 needs general answer, but I would like to emphasize the significance of snow cover. Everybody agrees that snow cover needs to be included in the hydrological modeling, but it influences, but to what degree? How improving information of snow will improve results of hydrological modeling? I am not sure that the answer to that question is known. There is a lot of hydrological presentation and projects taking snow into consideration, and they all are developing those projects independently. And it is quite possible that the same product have different accuracy in different projects. And it is desirable, it could be recommended to make intercomparison. And make intercomparison not only in algorithm, but also in initial sensor information. Because using different sensors, unfortunately, could lead to different results, to different in different projects. And analysis of these differences is not trivial. It's not just estimate by comparison with ground truth or intercomparison between different products. To understand the difference in the results following from different interpretation of snow observations needs, I believe, special, maybe not very significant, but special experiment. The goal of which is to understand reason of those differences. And the second point, I just want to mention 2 points.
Maybe for this, we'll maybe answer for the snow first. So the snow cover, I think, has most impact on land-atmosphere interactions. But once you go to snow depth and then amount of SWE, I think there has been several presentations that have shown that it actually does improve the hydrology. If you get the snowpack right, snow melt will improve, and then the discharge is improved, I think.
And as a quick answer to your question about the intercomparison, ESA and actually as ESPN and Bolden is here, they launched this week the hydrology cluster, and the idea is actually at first we need to know that the data are there, and second, basically with the cluster, basically the idea is that probably now we know that for instance over Alps there are several satellite products for snow water equivalents. It will be likely that a project for intercomparison will be there.
Okay, before going to the clusters, I would like to mention my second point, if it's appropriate. Yes, everybody needs snow information for hydrological studies, but it is understandable that snow information is equal to snow water equivalent for hydrology. But Peter mentioned he lacks energy. Snow influences heat exchange at the very least at the surface, and it's taken into account. But in many areas, snow does not take 100% of coverage. There is as such, I'm afraid to say that F starting word, snow fraction. And snow fraction is a big problem, and it's a gap in knowledge, not in hydrological knowledge, but in cryosphere knowledge. Because snow fraction, you know that snow could exist in mountains when temperature is more than 20 degrees centigrade. And it's tremendously influenced heat exchange, and heat exchange, it obviously influences water mass exchange. At the moment, there is no global reliable information about snow fraction that influence not current cryosphere problem, but it creates problem for global hydrological studies. And that is a gap in our approach. And I know example, then different models create excellent close to 100% estimates, but magnitudes of fractions significant up to 40%. So it is a lot of problem, and it influences not only hydrological, but many other land surface parameters. And for large part of the
So
land
snow
surface.
is important, and we have to consider it carefully.
Snow fraction.
Snow fraction.
Yes, emphasis.
And
And
so
now
I think there is the IMS snow fraction product, which comes at a fine resolution. So if you, it's all a matter of scale. So if you then you upscale it, say from 200 meter to 1 kilometer, then you have a snow fraction product. Because it starts with a binary 1-0 at a high resolution, and then if you upscale it, it's a snow fraction. So that's one global product. But I know, and I don't think the person is in the room, but Thomas from
Thomas
NGO,
left.
Thomas Nagler, he has produced several snow cover fraction products from ABHRR, from Modus. So there's several products around, I think.
Are they comparable? Are they good? Yes, he produced many of them. And I know other authors. IMS is not related to fraction at snow fraction at all, as I understand. It provides, yes, binary snow at 4 kilometer or at high result.
No. Even Modus is 250 meter, 1-0. And then if you aggregate for 500 meter, you yeah, Modus is 200.
No, Modus provided snow fraction in exercise number 6. And I don't know why. We're in interested time living. NASA stopped providing snow information completely. And Sentinel-3 did not even start to try and provide snow information. It's very interesting and strange, difficult to understand. And speaking last point about clusters. Why do you think that clusters will change anything?
No.
It will be the same project.
Will help too.
Excuse me?
Will help to do something together.
But it will be realization, implementation. It will be the same projects, the same consortium doing the same job under the different title.
Not
For
necessarily.
that, maybe we can give the word to Aspen. I think he's in the room and he knows the exact answer.
Yesterday or the day before, yeah. Of course, it will be a bit of the same, but it will be bigger consortium way that we will have several projects working together. Maybe we will have some extra funding that 2 ESA projects and 1 EC project will work together on a certain issue that they were not able to do as separate projects. If you say that then this becomes a new project, yes, I agree. But the difference is maybe that we can, inside this cluster, we can define with a larger community what is really the issue to address. That is maybe not so that we can work on the correct issue, which is not maybe so easy that it happens when there are calls from the Commission or from the ESA. that has not been so much discussed with the community before. But now we have existing project. They see really what is an issue, and then we can address that very quickly by grouping together different projects. That's the spirit of it. But as you can say it's just a new consortium. But yes.
Deadline
I think we have always tried to do that through workshops like this. I mean, that has been the approach of ESA. At least we organize workshops together with the scientific community, and we have discussions during these workshops where we try to identify what are the major topics that we should address in the next years, and then we try from ESA side to make some ITTs for that. But then we may, for example, we may have an ESA project where we can do 90% on the Earth observation part, but we cannot really do much on the modeling part. We can do so much on the in situ part. So the goal is then that if we put ESA projects together with the commission projects can work on the in situ and on the modeling part. Then by bringing these projects together, we can more adequately address some of the issues. That's a bit the spirit behind, because before we had ESA calls focusing on Earth observation, and commission, they could also focus on Earth observation, but then also on more on the modeling and in situ, making this cluster through the cluster, making collaboration between ESA and ESA projects. We can better address such issues because we can work both with a big effort on Earth observation part, but also on the modeling and on the in situ. I think that was kind of a key driver or key motivation for these clusters.
It's all about the synergy. Thanks a lot, Espen. And I think Diego is waiting.
It's probably related to something that we were talking a bit of a while ago already. And it was about the information flow and so on. I think Peter is still here, right? So I was just thinking that the way I see the observations in the DTEs and so on, it feels like it's either as a view as a way to benchmark models, physical models, or as an input to physical models. We have another way of actually looking at observations and learn a lot from them. I'm not thinking about machine learning, but more like causal inference methods. Today we saw a blink of it, which is correlations from Emmanuel, right? But there is a lot of information that can be extracted about how variables are related, at which scales and so on, without physical models. That tells us a lot about the physical system. I'm just wondering the degree to which we should incorporate that in DTEs. Plenty of information theory methods on causal inference, but also based on many other theories that could be actually implemented into a DTE and reveal links between variables that can teach us quite a lot about physical system without assumptions in regards to the physical model. So just a comment on that.
To my understanding, ESA with the DTE program is trying to do this, because the same is not done by the destination Earth activities, because destination Earth activities, they will run their model and they have to be operational and they have to make something. ESA, in principle, with these components, try to understand not actually how to improve Earth system models, and this is one of the ways. Understanding actually what is happening physically and with Earth observation, and this is my understanding. As Espen is saying yes, so here, so as ESA is.
Question?
A very quick comment, maybe on the first sentence. Probably we should also think before to answer how to answer this question, what we don't know about the water cycle, and then when we know the challenges, maybe we can also understand how the digital twin Earth can solve this, or whether how we could use that observation, which Earth observation, how we use in the models. And so I think it's very important to know that the challenges of the water cycle exactly, and then probably we have a clear idea of how to address them.
This morning in one of the sessions, because actually we are discussing about what is known and what is not. We have discussed about this about a bit, and was asked by, for instance, Ilas Daras from ESA. One of the answers was water in underground water, and the other answer was human impact. Simple to try to summarize. But then, of course, to me, there are also many physical processes that we really don't catch, because all the models do the same, but actually it doesn't mean that they do correctly. But these two are much, for it, groundwater is, we don't see below the ground, so it's very difficult. And human impact is depending on our behavior, that is not, it's random. And the physics is a bit less random. But probably there is something else.
I just have a comment on what Peter brought up regarding machine learning and deep learning methods not being interpretable. And I agree that in the current state, they're very non-interpretable, which makes their use difficult for any scientific application. But I feel that this is not a limitation that might continue into the future. The fact is that most of these models were designed for tasks where interpretability was not a large factor. So they were designed for vision tasks and things like this by large companies that don't care about interpretability. But this doesn't mean that you can't design models that are interpretable. And so I think if the scientific community embraces them further and starts adopting them and designing them differently, perhaps in the future we can see models that incorporate interpretability into them, which will then improve their benefit to the scientific community. Yeah.
Something is already out already, and that's telling ourselves that the machine learning is not interpretable, and so we cannot use. Probably we have to stop to say, because people using machine learning that they have the knowledge on how they use machine learning, they start using this start talking about interpretability to basically develop machine learning techniques that basically can be explainable, all these kind of things. Still, we have to understand ourselves also, because for black box probably is not anymore the correct term that we should use for machine learning. But not only hybrid, it's
I need some physical description in order to interpret. Yes, you do. That's not what I said. I said you need a physical model. Well, you need a physical model that explains what it is, right? No, that's where I disagree. Yeah, but then you use the human as basically your physical model, right? so I mean, then you're talking about translation. And so again, you're still looking at a physical representation, and it might be a mental one, but it's still a physical representation. So, but I didn't want to go there. I actually want to go somewhere else quickly, if I may. And then I'll shut up for the rest of the afternoon. One thing that might also be useful, and this is a completely different tack, is we haven't talked really about data assessments and a little bit about benchmarking. I'm not sure who brought that up, but yeah. So that, but data assessment is one thing that I think is so fundamentally useful and so undervalued in the sense of support. But if we really want to better our EO data and understand what our data is, then we need assessments, and not in terms of which data set is the best, but really in terms of how is this data applicable? What does it represent? What are the boundaries? What are the constraints, et cetera, et cetera. So when we now talk with about altimetry data and all the different types of data sets are coming up, it's a great opportunity to also think about what type of framework do you want to use to really do the assessments. And we have a couple already there. Water vapor is one, precipitation is another one. There are quite a few around, and I think that's a good way to really get a better insight into what these data sets are. I'm not sure how many of you are aware of like the International Precipitation Working Group that has a report out on precipitation data sets. Super useful. It's, yeah, okay, you don't count. But it's not well known enough. And I think that's our fault. I mean, we're not pushing it hard enough.
Well, one of the problems is that actually the number of data set that is going up is exploding, and
Yeah,
that assessment is becoming. When I started, I made the assessment of all this and most of the product. If you, I'm trying to make something similar, but it's really hard.
Yeah, and this is also where actually digital twins can be become very useful at some point. But that's a little further in the future, I think. But yeah, you're right. I mean, that's also in itself a problem. And by actually doing assessment, making choices, then at least there is a group, a set out there that is well understood and is relatable, and you know what they represent. Precipitation is a nice example. 20 years ago, there were 2 or 3. I think there are now like 60, 70 global data sets, and I don't know how many regional ones. So yeah.
Before we went silent.
Sorry.
What does this mean?
What I'm saying is you compare the various data sets and see what their constraints are, whether you're applicable. You describe all the resolutions, temporal, spatial, radiometric. You see that, in the broader sense, really describe the data sets and relate them to each other and see where they're applicable. That's basically what an assessment is for us. None of them do.
I put the main bullet points. We can write something. You put something together. Yeah. Sounds good.
We are actually out of time.
Okay. Okay. I just wanted to say something.
How to taxi? No. We have to. I have to leave actually, but you can continue to discuss if you want.
There were 2 days of validation of altimetry data. And if you have someone of this group of altimetry data, this is why I ask you if you have tie gauges or gauges in a reservoir. So
Probably Peter is trying to find something really kind of group that to do the validation independently of, for instance, all the altimetry data. Not everybody is assessing his own product. This is kind of initiative that help us to really have an assessment of the product independently and let's say honestly. I will say thank you very much for coming to this last session today, and see you around in the future.
Thank you. It's okay. You did very well. Have a good trip back. Sorry to hear.